to the organizers, and thanks for that introduction. So before I begin, I want to acknowledge that it's Martin Luther King Jr. Day in honor of Dr. Martin Luther King Jr., and I thought I would read a quote from his acceptance speech for the Nobel Peace Prize. This was in late 1964 in Oslo. This is an excerpt, and I apologize for having to excerpt the speech. Previous to this, he's sort of wondering why he's being awarded this prize now when he feels like that the work that he's been doing, the advocacy, is still very much underway and hasn't quite achieved all of its aims. But anyway, I like this section. I accept this award today with an abiding faith in America and an audacious faith in the future of mankind. I refuse to accept despair as the final response to the ambiguities of history. I refuse to accept the idea that the isness of man's present nature makes him morally incapable of reaching for the internal oughtness that forever confronts him. I refuse to accept the idea that man is mere flotsam and jetsam in the river of life, unable to influence the unfolding events which surround him. I refuse to accept the view that mankind is so tragically bound to the starless midnight of racism and war, bright daybreak of peace and brotherhood can never become a reality. I have the audacity to believe that peoples everywhere can have 3 meals a day for their bodies, education and dignity, equality and freedom for their spirits. I believe that what self-centered men have torn down, men other-centered can build up. I believe that we shall overcome. This faith can give us courage to face the uncertainties of the future. It will give our tired feet new strength as we continue our forward stride toward the city of freedom. When our days become dreary with low hovering clouds and our nights become darker than 1,000 midnights, we will know that we are living in the creative turmoil of a genuine civilization struggling to be born. So I thought that might be a nice sentiment to start. Growing up in the US, we learn about Dr. Martin Luther King as a hero of the civil rights struggle. But something I only learned as an adult is that in his time, he was quite a controversial and divisive figure. And anyway, but of course, a real inspiration. So I don't have a great transition from that to what I'm actually going to talk about, but except to say that this is one of the very few federal holidays we have in the US, and I appreciate your time and being mindful of your time. I'll get going. Okay, so I'm maybe representing the mathematical community in this conference. I'm an emissary from the mathematical community, and folks here who are experts on certified programs and proofs might be aware that mathematicians are increasingly excited about prospects of computer formalization to tackle really cutting-edge, interesting mathematics. So I thought I'd highlight some sort of recent successes that involve either very long and difficult proofs with a lot of technical detail, like the odd-order theorem, can help resolve ambiguities in the refereeing process. So the FlySpec project, which was launched by Tom Hales to formalize his proof with Ferguson of the Kepler conjecture, was in part born out of frustration from the human trying to certify that the proof was 100% correct. Famously, Peter Schulze proposed a liquid tensor experiment where he challenged the formalization community to verify a proof that he wasn't sure about and wasn't sure that anybody else would actually check because it was sort of so technical. And a final recent achievement is a formalization of something called the Brunery number. This is a bit different flavor than the other things. What was actually formalized in cubical agda is a proof that something called the fourth homotopy group of the 3-sphere, so this is some algebraic invariant of a topological space, was Z mod nz for some n. So this was a proof in Guillaume Brunery's PhD thesis in a cubical variant of homotopy theory that satisfies, I can never remember if I'm supposed to say normalization or canonicity, but the thing that means that each natural number has a canonical form. And so then Axel Lundström and Anders Mortberg, formalizers, asked cubical agda what n was, and they said that n is -2, which is wonderful because that was correct but unexpected. So -2z is isomorphic to z mod 2z, so -2 was the correct answer, and unpacking the mathematical construction, one could see that it would have been -2. They were expecting the answer to be n equals 2. Okay, so what I actually want to talk about is the 2 formalization projects that were mentioned in the introduction, both of which have been launched since then. So the efforts I highlighted on the previous page were concluded in 2022. more recently, I've become curious about what it would take to formalize results in my own field, which is something called infinite dimensional category theory. And I think there are some in formalizing results in infinite dimensional category theory. And so the first part of this talk, I'm going to try to keep this at a high level because it's difficult enough to explain to a mathematician what an infinity category is. A lot of mathematicians are intimidated by infinity categories, and I don't want to get bogged down in the mathematics. So speaking somewhat metaphorically and at a very high level, I'm going to try and describe some of the particular challenges of taking a recent paper in the infinity categories literature and giving a computer verification of it, so formalizing any of its results. And then I'm going to describe the two particular projects that are attempting to do this, not yet for the sort of cutting edge literature, but at least for the background theory that would be necessary to even formalize the statements from the literature. The first one is in Lean. This is being co-led by Mario Carnero and Dominic Verity. The second is in RESC, or RZK, proof assistant written by Nikolai Kudasov. Jonathan Weinberger helped launch that project and spoke about it here last year. Okay, so let's go ahead and begin. So I'm going to use a metaphor to describe what makes the literature in infinity category theory a little bit more challenging to formalize. This metaphor doesn't quite fit, and so I should apologize to Terry Tao at this stage. But nevertheless, this is an interesting idea, so let's discuss it. So he has a famous blog post from maybe a decade ago titled "There's More to Mathematics Than Rigor and Proofs," that describes mathematical education into three stages. There's a pre-stage where mathematics is sort of informal, arguments are sort of fuzzy, intuitive, hand-waving. We don't necessarily have precise definitions. The emphasis is more on computation and theory. Then there's the rigorous stage, which is what in the US somebody would encounter only in the course of doing a mathematics degree at university. Maybe in other parts of the world it's touched a little bit. And one is taught that in order to do maths properly, one can think in a much more precise and formal manner. The emphasis is primarily on theory. One is expected to be able to comfortably manipulate abstract mathematical objects without focusing too much on what such objects actually mean. This could occupy the later undergraduate and early graduate years. That's maybe the stage that's sort of closest to formalization, but still mathematics is pretty informal. And in the US, you're not really taught necessarily logic, sort of formal logic. And so I like to acknowledge that when I earned my PhD, I could not have stated the axioms of set theory. I might be able to do it now. So rigorous stage. And one has grown comfortable with all the rigorous foundations of one chosen field and is now ready to revisit and define rigorous intuition on the subject, but this time with the intuition solidly buttressed by rigorous theory. So the emphasis is now on applications, intuition, and the big picture. The stage usually occupies the graduate years and beyond. And for Tao, this is really an aspiration. This is an ideal state to reach where every heuristic argument naturally suggests its rigorous counterpart and vice versa, where one's intuitions are so refined that one can dream in heuristics and then later verify that dream through a rigorous proof. So I'm going to use this as a metaphor to describe some of what's going on in the literature of infinity category theory. Again, it doesn't quite fit, but what does seem to be common is arguments are not always explained in full detail. Some claims made as part might not quite be true as stated, but nevertheless, most of the results are basically right. So proofs with gaps or errors are often what's called morally correct. So there's, contain an important idea, and that important idea, even if the proof that was written in some cases published, is not the correct proof. And in particular, proofs in the literature may rely on sort of incomplete definitions, sketched arguments, or explicit unproven conjectures. And I'll illustrate now with some sort of case studies of this from the literature. The notion of infinity category sort of has a long history, but maybe in its modern form, 2003 preprint on infinity topoi. This is the precursor to Jacob Lurie's book, Hyotropics Theory. And what's interesting about that preprint, which can be found on the archive, is it avoids using a precise definition of an infinity category. So this is a 100-page paper that is in background theory of infinity categories to be used to do something else. derived algebraic geometry, but it doesn't sort of start the way that mathematicians are comfortable, which is here's a definition, and now from this definition we can prove what. So paralleling Jacob Lurie, I'm going to avoid telling you what an infinity category is right now. Very weakly, very roughly, it's a weak infinite dimensional category. Here's what Lurie actually writes. So we will begin in section 1 with a theory of infinity categories. This theory that didn't really exist at the time. There are many approaches to the foundation of the subjects, each having its own particular merits rather than singular. One of those foundations here, we shall attempt to explain the ideas involved and how to work with them. The hope is that this will render this paper readable to a wider audience, while experts will be able to fill in the details missing from our exposition in whatever framework they happen to prefer. The parlance of the field, one uses the term model to describe a precise definition in the traditional foundations of set theory and logic of an infinity category theory. This is what Lurie is trying to avoid using. And a paragraph like this is very common. A lot of papers in the field start exactly this way. However, the book Higher Topos, the long version of this paper, doesn't read this way. Pushback from the community, how can we be doing rigorous mathematics if we aren't even starting from a clear definition? And so Lurie does pick a model in that book. But what's interesting about this is this is sort of the perspective that experts in the field would often prefer to take. So work without an explicit definition. Maybe for aesthetic reasons, maybe because it's so far from their intuition somehow. Okay, so another example called the cobordism hypothesis. This is explaining a little bit about but in an expository article on the subject, Dan Fried writes, this was conjectured by Baez and Dolan in the mid-1990s. It has now been proved by Hopkins-Lurie in dimension 2 and by Lurie in higher dimensions. There are many complicated foundational issues which lie beyond the definitions in the proofs, and only a detailed sketch has appeared so far. And what the footnote elaborates is that nevertheless we use synonyms in this manuscript. The foundations are rapidly being filled in, and alternative proofs have also been carried out, though none has yet appeared in print. And so this is like a fun question to ask among your friends in the field: has the cobordism hypothesis been proven? And nobody has any clue, few people are willing to go on the record because, of course, so the preprint of Lurie that Fried is referring to. Very beautiful ideas and has a lot of gaps in it. And so is that a proof? What is sort of the status of the mathematics here? Does it make sense to try to prove the cobordism hypothesis? And this is uncomfortable for mathematicians, of course. We like to think that our proofs are black and white. But this is an instance that certainly is not. Okay, so another example. A lot of what infinity category theory is for something called derived algebraic geometry, which is a hard version of modern algebra. There's a 2-volume series that was published in the Society in the last few years by Gates-Goy and Rosenbluth. It runs to nearly 1,000 pages. And much of this first volume is devoted to developing the necessarily preliminary results I was trying to avoid this, but when I say infinity category, that's really a nickname for what's more properly called an infinity category. And then there's other versions of weak infinite dimensional categories called infinity 2 categories. It includes this following disclaimer. Unfortunately, the existing literature on infinity 2 categories does not contain the proofs of all the statements we need. We decided to leave some of the statements unproved and supply the corresponding proofs elsewhere, including the proofs here would have altered the order of exposition and would have come at the expense of clarity. And then there's a sort of a clear list of 7 unproven statements. So, so here's a massive book that's resting on conjectures largely, and nevertheless is an important contribution to the field. And the final example, perhaps the most famous of all of those, is from a 1991 paper of Kapronov and Voivodsky. Concerns something called the homotopy hypothesis. Again, I'll avoid discussing the mathematics, but gives a precise definition of an infinity groupoid, which is closely related to an infinity category, and aims to connect it with something from topology called a homotopy type. And this paper contains, it's relatively short, maybe 18 or 19 pages by mathematics standards. We don't tend to have page limits in our journal publications. But 7 years later, Carlos Simpson posted a preprint which shows that a particular homotopy type cannot be realized by a particular three groupoid, so a truncated version of an infinity groupoid, and this contradicts clearly the statement in the infinity or in the corollary, the last corollary in this paper. But what was confusing about it is Simpson could not identify where Pranoff and Voivodsky went wrong in their proof, and Voivodsky, at least, who's the one who's the source of this anecdote, who's written about this, says he thought that the sort of obstruction that Simpson is identifying with in their argument. So it was very obvious from the two statements of mathematics, but neither party could whose proof was wrong. And Voivodsky said, I was sure we were right until the fall of 2013, so 15 whole years later. And this and another sort of famous mistake in some of Voivodsky's Field's metal work on motivic homotopy theory actually led him to abandon pen and paper mathematics and pursue computer formalization. So, and in fact, pursue computer formalization in a novel foundation system, which is something that I'll come back to a little bit later. Essentially because he didn't trust the mathematical community, because he had such a strong reputation, because he earned a Fields Medal in 2002, he didn't trust the mathematical community to check his proofs at least quickly enough. Mistakes discovered eventually. Like a working mathematician, I guess you want to know as soon as possible, and so turn to computer formalization. Okay, so here's the reason why I'm discussing these anecdotes is I want to think about the following question. So, how might this literature, and so I'm using infinity category theory both as my personal area of expertise, but also as a stand-in for other subfields of mathematics that are similarly complicated and technical and involve very long papers and involve very complicated definitions that aren't often stated in full. So there are areas of mathematics that are like that. There are other areas of mathematics that are not like that. But how might this literature read differently in a future where mathematicians are expected to work interactively with a computer proof assistant? So is it possible to use a computer proof assistant if your literature is sort of post-rigorous? It's not explaining everything all the way down to the foundations. How could you possibly formalize something like that? So I don't think the prospects are quite as bleak as you might think. On the one hand, it's desirable to give a precise construction of a mathematical notion of an infinity category. So that was the preprint on infinity topoi. The desire was to develop this without a precise definition. One could instead axiomatize the necessary properties of an infinity category and then try to prove theorems regarding those properties and then hope that the theory is not vacuous. So eventually you would have to construct something that satisfies those properties, but maybe you could sort of black box that using this technique of axiomatization. That's quite a common technique in formalization as well. So a sketch proof, like the proof of the cobordism hypothesis, would be harder to implement because proof assistants tend to require some. But certainly if one made the effort to formalize a sketch, it would make it a lot in the proof. So Lean, for instance, and many other proof assistants allow saris, where you state a theorem but don't supply the proof yet. And one could imagine, this would be an appealing way to both reward the mathematicians who are involved in constructing the scaffolding, which is quite hard, a sketch program, but also reward the mathematicians who are involved in filling in the saris, so completing the details of the sketch that are required to make it true. I think that's a very important sort of sociological problem within mathematics, is figuring out a way to give credit to everybody who was involved in a team that's needed to achieve something difficult, like the cobordism hypothesis. The Gates-Square-Rosenblum book, Proof, Modulo, and Proven Conjectures, again, should be formalizable, providing that those conjectures are clearly stated in exactly the way that they are used. That, I think, more or less is what is happening, at least informally, in this book. And then finally, of course, an incorrect proof should not be formalizable, which is, of course, a good if every mathematical journal publication is required to come with a formalization, one would imagine that would cut down the rate of mistakes in the literature, though of course not completely eliminate them. Perhaps this process of formalization would help identify the error by calling attention to a subtle obstacle to be overcome. This last point is somehow persuasive, because the fundamental problem in the field is that, how do we formalize proofs in an area like my own, where the arguments tend to be long and complexity every step. So even today, his proof with Kapranoff of their claim of the coborders is the one that's a mistake, but still there's an active debate on precisely what the mistake is. There's I'm not one of the other long math overflow posts where mathematicians are still trying to figure out exactly what happened here. And it's, not that this is an obscure area that nobody's thought about for the last 30 years. This is a subject that is of central interest to people in the field. And nevertheless, it's just the ideas are so long and so complicated that no one's quite gotten to the bottom of it yet. So do we as a community really need to just slow down and do everything formally so that we don't make mistakes and every conjecture is, is proven correctly? We're eliminating the mistakes in the literature. How does that integrate with Tao's vision for post-rigorous mathematics, where some mathematicians are dreaming up vast research programs that are beyond what is provable, what is formalizable, but involving definitions that are not yet made precise, that then sort of lay the groundwork for the future? Do we all have to return to doing our mathematics rigorously in a computer proof assistant? I think that's an interesting question. And so more recently, I've been involved in some experiments to try and formalize some infinity category theory in a computer proof assistant. And I'll describe sort of three broad strategies for sort of proceeding nevertheless to try and get a toehold on this literature. So the first strategy I might call analytic, giving a precise definition of an infinity categorical notion in some model. So the probably most common model is something called quasi-categories, and prove theorems using the combinatorics of that model. So really start from a definition that is made precise in set theory and then tie every step of the argument down to the traditional foundations. A second strategy is this axiomatic one. So if it's objectionable to use this definition because somehow the aesthetics are wrong, or you're forced into considering combinatorial details that get in the way of understanding the ideas of a proof, instead we could axiomatize sort of the theory of infinity categories or the category of infinity categories. One approach to that is something called an infinity cosmos, which I developed with them. And then we could state and prove theorems about infinity categories in this axiomatic language, and then hope later to show that the theory is non-vacuous by proving that some model does satisfy the axioms, and formalize other examples as desired. And then a final strategy is the foundations. So really the fundamental problem here is that the basic notion of the field, an infinity category is just an awkward concept to define in the traditional set-based foundations of mathematics. An infinity category, I realize I still haven't given you a definition, but it just doesn't involve a lot of sets. And so perhaps we could develop some sort of domain-specific formal language, domain-specific type theory that allows one to have primitive objects that are much closer to infinity categories, to think about infinity categories synthetically. So one would then need a computer proof assistant that implements that specific foundation, that knows the rules of that formal system. So this couldn't be done in something like Lean, but it could be done in an experimental proof assistant, for instance, something like Rusk. And so what I'll do now is describe, so I don't know of anybody who's really working, well, sorry, there are a lot of individuals who are working on strategy one. I don't know of sort of a large group effort towards strategy one, but I've been involved in projects working towards strategy two and strategy three, and I'll talk about those in turn. To the organizers, does it make sense to pause for questions now, or? might be better. Sure, no problem. Does anybody want to ask a question before we get into the projects? Sure.
What's the difference exactly? What's the difference exactly between strategy 2 and strategy 3? Because it looks like similar to me.
Great. So thanks for that question. So in the past, I've described both strategy 2 and strategy 3 as synthetic in opposition to the analytic strategy, which is strategy. The difference is that strategy 2 is something that's implemented in traditional foundations. Really, it's independent type theory because lean is independent type theory. Lean and, well, the definition of an infinity cosmos is stated in the language of ZFC, whereas in strategy 3, we're giving a definition of infinity categories that is not interpreted in ZFC, but in something else. Explicitly, it's a simplicial extension of homotopy type theory. So it's whether we're working in traditional foundations, whether we understand that as set theory and logic, or Martin-Loop-dependent type theory with extensional identity types, or whether we're working in some exotic foundation that's optimized to be the foundation for all mathematics.
Well, maybe this question's a bit premature and you'll get to this, but this third strategy, something like cubical AGDA, they take different foundations and tweak AGDA so that but cubical AGDA wouldn't be something that this would fit.
Yes, so great. So yeah, the sort of proof assistant you should think about for strategy is something like cubical AGDA. So cubical AGDA is implementing a theory, cubical analog of homotopy type theory. It's not cubical AGDA. It's of it that is, I don't believe, implementable in cubical AGDA, but there's some cubical AGDA experts here. You could ask about that later. But something like cubical AGDA. No. Yeah.
Yeah, so also for strategy 3, how do you then address the gap between the bespoke proof assistant and then the theory of that type system, and then showing that is actually modeling the set-based models?
Right. So you're anticipating a question that appears on the final slide. So on paper, we do understand the semantics of this system. So on paper, I believe it, but has any of that been formalized? No. So, okay. Great. Let's dive in. So okay, so this first project is a formalization project in Lean. It's relatively new. It was launched just this past fall, co-led by Mario, who's here, Dominic Verity, and myself. And the objective is to formalize a particular axiomatic approach to infinity category theory in Lean's mathematics library. So the advantage is we get to take advantage of this large library that exists already. So there's sort of a common workflow used for Lean formalization projects that was developed initially by Patrick Massot. Pietro Montecone is the one who helped us set it up for this. So there's a website, link is there. The website hosts both the Lean Kyle's are a copy, relatively up-to-date copy of Math plus. There's also something called a blueprint, what that is, created from a LaTeX file that's annotated with tags that connect definitions and theorems to formalizations where they exist and indicate dependencies in any case. This produces a dependency graph, which will indicate which results are ready to be formalized, not yet ready to be formalized, in process of being formalized, and so on. And then we have our own channel on the Lean Zulip chat where we discuss all of these. So this is Lean formalization projects. I'm going to get a little bit into the mathematics to try and describe now the idea of this project. So this is the Lean definition of an ordinary one category, so as ordinary category. So in Lean, types are sets for those who distinguish between those notions. So it has a type or set of objects V. Then it has a dependent type of arrows. So between any two objects x and y, there's a type hom xy of arrows from x to y. There's two different notations for that in lean, unfortunately. So there's COMXY notation, and there's also X long arrow Y. They both appear on this slide. And then it makes that into a category as additional action. So the data involves a specified identity arrow X to X for every X, a composition function that takes an arrow from X to Y and Y to Z and composes return from X to Z, rules about identity laws and associativity and so on. Okay, so this is the definition that exists in lean. So the idea of an infinity category is just to replace all these types by something called an infinity. These are also known as types. This also known as anima. It's essentially the information of a topological space encoded by its homotopy groups. Probably weaken all the structures. What's you can't do, though, is just implement that sketch in this sort of style. So part of it would involve a sort of infinite amount of data. So we have not only objects and arrows, which you might think of as arrows between arrows, and all the way up. But sort of the main issue is really this weakening. So there's really sort of no longer a canonical identity arrow necessarily, or a canonical composition function. Instead, there's a whole bunch of different things that are equally well could be considered as the composite of two different arrows in dimension 5, for instance. And either arbitrary choices and then exhibit a bunch of additional data that exhibits that those choices are suitably coherent, or avoid making the choices and then argue that these things are sort of suitable and deal with the fact that you're sort of placing some sort of homotopically unique relation. So no definition style. This in and in fact is already in MathLib is a sort of an analytic version of this. So this is a precise definition that's easy to state in traditional foundations that does capture this idea. This is something known as a quasi-category, and here's the definition, which I'm not going to explain at all. The thing that I want to emphasize is that how this relates to the idea on the previous page is not at all clear. So the idea on the previous page is that an infinity category should be just like an ordinary category, except you replace all these sets by infinity groupoids. An infinity groupoid, by the way, is a complex which has some sort of similar analytic definition, and explaining sort of what the infinity groupoid of objects in a quasi-category is, or what the infinity groupoid of morphisms between two objects, or what the infinity groupoidal composition functions are. I mean, these constructions are all a bit complicated. They're certainly known to the expert field, they're known on paper, but none of this has been formalized. And just the fact that all of these very basic things are a little bit fiddly is the main challenge of this approach to formalization. Involved in every single thing that you want to do. And a sort of fun illustration of the fact that, like, basically no theory of infinity categories using quasi-categories have been formalized. These MathLib for at least a year is actually only last week. Joël Rioux discovered that the definition of con-complex it included it included an extra horn that should not have been there. And if had anybody done anything with this definition at all, we would have discovered that, because there would be no example. None of the known examples of con-complexes would have satisfied that definition. So anyway, I think that's pretty funny. Okay, what are we doing instead? So the idea is that we're going to leverage some of the existing results that have been formalized in MathLib. So not stuff about infinity category theory, but stuff about other versions of category theory. So there's a lot of ordinary category theory in MathLib. There's also some development of category theory. There's also some enriched category theory. And we're going to, as much as possible, lean on those existing results to formalize some infinity category theory. And the way this is achievable is that by abstracting the theory of infinity categories using this axiomatic notion called an infinity cosmos. And what it is in particular is it's a particular sort of enriched category whose objects are infinity categories. And from particular 2 category, whose objects are infinity categories, whose morphisms are infinity functors, whose 2 cells are infinity natural transformations. This is an analogy to a 2 category whose objects are ordinary categories, ordinary functors, ordinary natural transformations. And some of the theory of infinity, so adjunctions, limits, con-extensions can be defined just using this 2 category, and in fact, some of these definitions are already in MATLib. So this is sort of a geodesic to some significant mathematics results. What will be difficult is sort of showing that any of this is non-vacuous. So, for this to really apply to an actual infinity categories, we need to connect it at some stage back to one of these models, one of these sort of analytic versions, and proving that quasi-categories finds an infinity cosmos will be quite difficult. But my vision is that we'll create sort of a bounty of this, a bunch of theorems that will follow as corollaries, and there are people who are working on pieces of this. Jack McEwen is close to one of the important steps, and so I think this will be achievable, maybe with sufficient motivation, and the sort of technical homotopy coherence work would be done in showing that this analytic notion satisfies these axioms rather than every single proof of every single thing. That's the vision in any case. So we started this project in September, and the first aim was just to formalize the definition of an infinity cosmos. So it's a particular sort of enriched category, but it involves particular sorts of enriched limits. Those limits do not yet exist in MATLib, and that's what we've done. So here's the full definition. I'm not going to attempt to read it, but it's not, well, it's not terrible, though of course it refers to some concepts that we also had to formalize. Another thing that we've been doing is I'm learning by some painful experience that if you try to wait till you finish the proof and then get to MATLib, it will never, actually the PR will never complete. So Mario and I formalized the proof that CAT has limits over the summer and that we're still trying to PR it. So we've been shipping things out right away. So this definition is not yet in MATLib. I don't know that anybody cares about it yet except us, but the supporting mathematics that went into this definition we have been PRing, so I'm pleased about that. Okay, so this I know is super technical, so I want to kind of conclude this section by coming back down to earth and mentioning some of the things that I've been unhappy about in the formalization so far that are at a lower level. So some challenges that I would love it if the real experts in computer proof assistance could help. So I think we're having a little bit more difficulty with lean than some people who are also trying to formalize quite technical mathematics and other subject areas are, and I'll mention 2 instances of that. So one of the things that Mario and I did, so this is something that we've formalized that is in MATLib right now, is a particular adjunction involving some of the free category and underlying reflexive quiver functors. So it's an adjunction between particular categories. What's distinct, so one of these categories is CAT, and the other one is this category of reflexive quivers. And in both cases, the objects are sort of type classes that represent some sort of more elaborate structure. So it's the type of objects that has by inference, some sort of category structure attached to it, and so on and so forth. And this seems to be very confusing for lean. So there's kind of 2 perspectives on a functor. Often, either in lean or in mathematics, sometimes you think of a functor as being a very big thing. You have some sort of big category, some mathematical world that you're working in, and you use a functor to transport into some other category. From the perspective of this formalization, a functor is a pretty small thing. It's just a morphism in the category of categories, and going back and forth between those 2 perspectives seems to be very confusing. So what I've circled here are all of the, so this is a proof that some diagram in the category of categories, some composite in the category of categories is equal to some other functor in the category of categories. That's what this is a proof of. And highlighted are all the steps that I think are unnecessary. So telling lean essentially that a functor is a functor and a composite of functors is a composite of functors and the identity functor is the identity functor. And really I need to interpret this as a morphism between reflexive quivers and not just between the underlying types and so on and so forth. So these are the steps that I would love to get rid of. This is the thing that not a domain expert who's not an expert in form never been able to write this. You know, I needed Mario to come up with any of this code. Okay, so another challenge, so we're in the phase of the Infinity Cosmos project where we're trying to construct this 2 category of infinity categories. And once we're there, then we just apply proofs from 2 category theory to develop infinity category theory. For that's great, and I don't know how easy that'll be in formalization, sort of for the following reason. So, you know, lean is really based on dependent type theory, and let me start with paper. So on paper, a 2 category has something called a 2 cell. These are these sort of 2-dimensional arrows that I've drawn here. And a 2 cell has a boundary involving some 1 cells. Those are the 1-dimensional arrows and some objects. And in lean, these 2 cells belong to a dependent type indexed by these boundary 1 cells and then also by the boundary objects. And on paper, when you see a picture like this, you can just sort of look at it and say, well, all the 1 cells sort of point in the same direction and all the 2 cells point in the same direction. So main theorem in 2 category theories, there's a unique composite 2 cell encoded by this pacing diagram. But in lean, it's not even clear that sort of 2 cells that are in this diagram are composable with one another because they belong, because there's sort of a non-trivial equality between the boundary 1 cells in sort of the case that I've highlighted here. So over the summer, I wanted to formalize a proof that if you have this particular pasting diagram and the etas and epsilons are the units and co-units of an adjustment, then in the middle, what you have is this eta 2 and epsilon 2, that's a unit, and it just cancels, is replaced by an identity and disappears. This some implication for something called the theory of mates. This is about vertical composition of mates. So this is a formalization in MATLAB, and I wasn't able to formalize a proof in that style because of this issue involving dependent types of sort of boundary equality, and you know, promoting those to data or transporting some 2 cells, something like that. Instead, I had to sort of pass to the components of the natural transformations, but that means that this than it should be. So we prove this for a particular 2 category of categories where 2 cells have components, but not for all 2 categories. So I mentioned this challenge in a talk last week at Lean Together, and this particular case has been solved, but there's a lot of cases like this, and in general, reason 2 cells is something that would be really and let me now go into the final project, so which is to explain this synthetic approach to infinity category theory and RESC, and then I'll take some questions at the end. So again, I explain a little bit of the sort of mathematical idea. So infinity categories are sort of like categories where sets are replaced with infinity group arrays, but it's just really difficult to turn that into a precise definition in the traditional foundations of mathematics. It takes a very long time to explain what an infinity groupoid is. That's what Kapranov and Voivodsky were trying to do in that paper, and we still don't know where they made a mistake. So it's hard to give a precise definition of an infinity groupoid. However, in other foundations, sort of type structure, type groupoids are actually the primitive notions, and in a foundation like that, infinity groupoid just as a primitive can actually give a definition of an infinity category that and is simple enough to communicate and with. You know, so all of this existing literature in classical foundations avoids using a definition of infinity category insofar as possible. By having the foundation do work, we can actually start from a definition, and now we're back in sort of more familiar terrain where we have a formal system, and then we formalize consequences of that definition in the formal system. This is how we do rigorous sort of undergraduate level mathematics, not the traditional foundations, but it's a more elaborate formal system that's a bit complicated to explain. So it's based on homotopy type theory. Specifically, I'm going to talk about a simplicial extension of homotopy type theory that has more elaborate context, and I'm not going to describe the formal system at all right here. That's the real obstacle here. It's not that we haven't described it. There's a paper with Mike Schulman where we have, but it just takes a very long time to describe it before you get to the good stuff. I'm going to skip over the formal system and get to the good stuff. So what is the, so I mean, the idea of it again is, this is actually just based on Martin Luff's dependent type theory, but with a different interpretation of the identity type family. We get rid of axiom K, so iterated identity types can be non-trivial all the way up. And there's a sense then in which a type is just like an infinity groupoid, where we can interpret the proofs of equality as paths, and then proofs of equality between equalities as homotopies, and that's where the higher structure comes. And in a particular extension, we equip each type with a second family of arrows. These are Hom types of an infinity groupoid, and so on and so forth. And in this, which I haven't described at all, I can actually define what an infinity category is. So what is it? It's a type, so a primitive notion in this elaborate formal system in which every pair of terms Hom from Y to Z, then there is a unique term of type Hom from X to Z that is a composite. So there's data in the witness of composition. Then there's a second condition connecting isomorphisms, which are defined using the category structure, using composition paths, which are the terms of the identity types. And so the low-level definition between familiarity with the system. And sort of a low-level explicit definition. What this has to do with identity categories, this is the expert aspect of it, which is that when we interpret the system back in traditional foundations, unique composite says that this moduli space of all composites is contractible, which is what is true. But within the formal system, composition function again. Collapsing the gap. My dream is that if we could do something like this, then we could actually teach infinity category theory to mathematics undergraduates, which would be nice for our colleagues in algebraic geometry and number theory and algebraic topology and other areas of theory, if this could be streamlined somehow. Okay, actually we can formalize, so that definition has been formalized, this whole system has been formalized. The proof written by Charles Rusk, who's the person who that most closely mirrors. This is really based on a model of infinity category, not the quasi-category model, but the Rusk space or complete system. What I really like about this approach is that we can already formalize much more complicated theorems about infinity categories than we can in the infinity project. So far in the infinity, we haven't formalized any theorems about infinity categories at all. But certainly, I hope we will by the end of the year. I mean, that project's a little bit newer than this one. But the innate lemma still seems pretty out of grasp. And this is, innate lemma is sort of the fundamental theorem of category theory. This is an explicit goal. Here we can formalize the proof, and it feels a lot more like the undergraduate Uneta, or the one categorical Uneta lemma. And it's because the formal system is sort of so powerful that we do a lot of work. So what I'm showing you here are, so the Uneta lemma says that some type is equivalent to some other type via explicit maps. And here are the definitions of those explicit maps. So given an ambient type, two terms, we can functions from Hom A, Z A to their partial transformations. It turns out that sort of naturality is for free. And given such a function, we can evaluate is A, and the arrow is the identity arrow, and that gives us an arrow from A to B. That's one map in Uneta equivalence. That's not difficult to write down in traditional foundations, but more difficult. An arbitrary arrow from little a to B. From this formal system, really what I'm defining here is a function between infinity grids element-wise, given an object and an object and an object. Here's a thing that is nowhere near defined. It's possible to give a definition like this that is not automatically, infinitely, coherently functorial. And so that's what's magical about the system. It makes it feel like I'm doing one category theory. more about this. Okay, so that was all a bit technical. I want to, well, here again we have junctions like this. At this stage, the cost of and sort of bring this talk back to a higher level. So it's really very painful to elaborate all these higher categorical proofs all the way down to the, if we're trying, are there enough people who are willing to help with some technical work? That's really the, am I going to have to like spend, 10,000 hours on this, or are people going to be willing to do this sort of stuff that is both complicated, it's it's expert level work, but technical. Lean is very powerful and it'll only become more so. There's a, as lean becomes more powerful, as boring technical proofs are replaced by tactics that can sort of automatically handle some of understand the proofs will the people who can apply these tactics be able to understand the proofs if they so right now we're able to prove that would be in lean, and the proofs are conceptual and short, but the formal system is unfamiliar, so convincing an expert that these are the correct proofs takes complete. Biggest problem with RZK various other things. In theory, you can formalize any theorem of infinity category theory in lean. That's not at all true, and it's the big issue. The question from the audience. A theorem formalized in RESC is completely useless to user of MATLib. Will we ever be able to do this so that somebody could do some derived algebraic geometry? Right now, it's not so helpful to have that in RESC. Formalization will involve a lot of specific formula systems. My experience is it is kind of nicer to use these synthetic languages, but we have these sort of AI-powered tools that really make it a lot easier to formalize in lean. Will that ever help cubical AGDA or some other sort of smaller experiment? In the production of formalized mathematics, sure, understand humans. Okay, I'll stop there. Thanks.
Thanks for the nice talk. I'm curious what your vision is for peer review of mechanized proofs. I think in the POPL community we kind of have this separation where we review the papers and we sort of trust that if they say, oh, all of these theorems have been mechanized, we accept the paper, and then we, after the fact, maybe do this artifact review process, but only after the paper's been accepted. So I'm curious how you see formalization changing the landscape both for us but also for the mathematics community.
Yeah, that's a great question. I only have one experience publishing within the there's aspects of it that function much better in mathematics. I mean, it's a real issue. A typical paper in this field will be 100 pages long and will involve some sort of sketched argument. So it's completely unfeasible for that something is correct. Getting papers reviewed at all, finding publication years. A lot of things are just languished as preprints forever because people just don't want to go through this. I could imagine is just sort of forcing authors to do a little bit more. So beyond mathematicians right now, and it is an important question. Of course, mistakes can be made in the formalized definitions, and but I think rather than complete formalizations, and it will definitely help us like clean up our act.
Yeah, I have a question. So the slide that you showed with like basically the analytic approach and then what you called like option 1 or option 2, I don't remember. So from a computer scientist perspective, this analytic approach, it looks a lot like if you think about set theory as kind of your machine code, then your option 1 is to define your abstraction basically at the level of machine code, and nobody wants to program machine code, which is why, like as you mentioned, that there's this quasi-category definition, and like maybe not a lot of things have been proved about it. Then option 1 is basically a high-level programming language, so you're mentioning Lean, and then option and so the Infinity Cosmos project that you mentioned, to me it looks like you're trying to define something like an embedded domain-specific language inside of a high-level language, which would be Lean here with its foundations. And then option 3 is basically defining your own programming language, essentially with its own foundation, with all of the project problems that of course causes to come about, like what you mentioned, that you can't maybe interoperate with other domains of mathematics that might use different foundations. So in general, for a lot of this talk, I had the idea that the way you're describing these problems in mathematics, they're becoming more and more just like things, like computer science problems. So how do you feel about that? Is that a development that you like, or are you apprehensive about it? How do you think mathematicians feel about this development?
Hey, sorry, your mic's not working.
My mic is off. Okay, apologies. Thanks for that translation. I appreciate it. I do feel a bit uneasy because I feel like now that I'm involved in formalization, I understand my work a lot. I mean, there's some senses in which I understand my work better. I understand proofs at a much more fine level of detail than I ever have before. But I feel more dependent on, frankly, the computer science community to achieve anything at all. And there's these issues that I'm running up against, and developing an API to support a definition that I just have absolutely no idea how to proceed. I think we are going to see a lot greater integration between mathematicians and computer scientists, because we absolutely cannot do any of this formalization of serious mathematics without a lot of help. And any work that you all can do to make yourselves easier for us to understand would be really wonderful, because yeah, I think a lot of people are kind of uncomfortable right now, and we don't want to just know that you've solved the problem, but we want to understand how you've solved the problem, because it's just very uncomfortable for us to be reliant on stuff that we don't understand to prove a theorem. So.
Anybody else?
So infinity groupoids are, of course, a special case of infinity categories. And so I was wondering, like, this seems like it should imply that a type theory with a model in quasi-categories should subsume a type theory with a model in, say, infinity groupoids. So are there any hurdles to this in practice? Like, if I have a proof in homotopy type theory, univalent type theory, does that immediately translate to a proof in something like RESC?
Right, I won't pretend to understand every possible way that you could develop a synthetic domain-specific language for type theory, but it is true that proofs in HOT are proofs in RZK. So, and the models of RZK are in particular infinity topoi, so places where HOT also has a model, they're infinity topoi of simplicial objects in an infinity topo, so so yes, but what you're saying is right. And one of the challenges in using RZK, so the language kind of looks like Agda, but it's a different type theory. We were not able to import HOT proofs from anywhere, so we had to spend a whole bunch of time reformalizing for ourselves a whole bunch of stuff in HOT to use as kind of the background, basically set theory and logic for what we were trying to actually do. So I'd be very happy to discuss some details of these proof assistants and the implementations in more detail later, but maybe that's a better one-on-one conversation. Thanks again.
Thank you, Mehdi. So we'll have the coffee break in 30 minutes. So I guess Emily will be happy to answer other questions during the coffee break. And now we go for remote talk, which was one of the distinguished papers CPP. I don't know if it's on live or registered. Has it been recorded before, or is it online? It's streamed online? And they are connected? I think they're working on it. Okay. So it's a paper about certifying rings of integers in number field. And yeah, perfect. So Anna is connected. Hello?
Hello.
Can you hear us? Yeah.
Uh,
Perfect. We can hear you, but we still can't see your slides.
yeah.
I guess they will appear at some point. Maybe not.
It was working a few minutes ago.
We just need to wait a bit and it will show up, hopefully.
You see.
Yes. Anna, maybe you can put your mic a bit up. We can't hear you very well.
Yeah. Oh. You still can't hear me?
Maybe your network connection is not that good.
Yeah. So I was having trouble with that, but then I moved. I tried a different network.
Maybe if you could try
And it was.
restarting the app,
Yeah.
that might fix the internet issues.
Yeah. Okay, you can see it now? And
Okay, it's working now. We can see your slides. Yeah, we
Okay.
still see a bit of the
Nice.
top bar at the top, but I guess it's okay. I mean,
yeah, but okay. Yeah, so I'm gonna talk about joint work with Anne Bannon and Sander Damen about certifying rings of integers in number fields. Can you hear me okay? Sorry, can you hear me?
yes, we can hear you, but we are trying to make
Okay.
your volume a bit higher.
Yeah, we're working on turning up the volume a bit, but we can hear you.
Okay. Okay, cool. So let me tell you a bit about the motivation of this problem. So many problems in number theory require explicit computations. And for example, one of these problems is solving some type of equations that we call Diophantine equations. And these are equations that we want to solve over the integers. And in order to do this, we need to compute explicit objects, such as the ring of integers of a number field or its discriminant. And I will tell you more about this a bit later. But in principle, we could use a computer algebra system to try to compute them. So for example, Sage Math or Mathematica. But the problem is that even though computer algebra systems are efficient, they are not always correct. So one of the aims of this project is to be able to verify in Lean the computation of one of these objects, which is the ring of integers of number fields. And the approach that we use is a certification approach. So we're going to use a computer algebra system, in our case, Sage Math, to compute a certificate. And and output Lean code with a proof that can be imported and checked in Lean. And we do this to formally verify some of the entries in the L functions and modular forms database. So to start with some definitions, a number field K is a finite field extension of the rational numbers Q. This means that K is itself a field that contains the rational numbers Q. And when we look at it as a vector space over Q, its degree is equal. So its dimension is finite, and we call this dimension the degree of K. So this definition was already in MATLib as a type class. So here are some examples of number fields. The rational numbers are a number field of degree 1. The rational numbers adjoin a square root of 3. This is a number field of degree 2. But I could also consider adjoining some root theta of a cubic polynomial like this one, x cubed minus 3x plus 10, to the rational numbers. And then I obtain expressions of this form. And this is going to be a number field of degree 3. So it turns out that any number field is isomorphic to Q adjoin a root alpha of a polynomial, an irrational polynomial over the rational numbers. So over the rationals modulo some polynomial f. Now inside these number fields, there exists a very special ring, which we call the ring of integers of K. And this is the analog of how Z, the integers, live inside the rational numbers. So to be more precise about the definition, the ring of integers of a number field K is defined as the integral closure of Z in K. What this means is that OK, the ring of integers of K, is going to be those elements x in K that are roots of a monic polynomial with integer coefficients. And just to recall, a monic polynomial is a polynomial that has a leading coefficient equal to 1. So this object is one of the foundational objects in algebraic number theory. And indeed, in MATLib, this has already been defined. You can see that the ring of integers of K is just the integral closure of Z in K. But this ring has a very nice property of having a Z basis. So this means that there is a collection of elements, say omega 1 to omega n, such that any element in this ring can be written in a unique form as a linear combination of these omegas, where the coefficients lie in Z. So some examples are the ring of integers of the rational numbers, which is just Z, as you would expect. The ring of integers of the rational numbers adjoin a square root of 3, and we obtain expressions of the form a plus b times the square root of 3, where now a and b are integers. And this is, we can also write it as Z adjoined the square root of 3. But it gets a bit more complicated when we consider higher degree examples. So for example, if we adjoin a root theta of the polynomial x cubed minus 3x plus 10 to the rational numbers, and we consider the ring of integers of this number field, we get expressions of this form. So we can see in this last example that 1 theta and theta minus theta squared divided by 2 is an integral basis for this number field. But we can see that in the second example, we were able to write this ring of integers as Z adjoined some other element, but it turns out that we cannot always do this. So in the case that OK cannot be written in this form, so Z adjoin some gamma, then we say that this ring of integers is not monogenic. So now that I gave you the basic definitions, let me describe the setup. So we have K, a number field that we obtain by adjoining a root of an irreducible monic polynomial with integer coefficients. And we can write this in Lean with the predicate is adjoin root K and then map something f. And this map, some map between Z and QF, what we're saying here is that we are considering this polynomial f, which lives which has coefficients over the integers. We're just going to consider it as a polynomial over the rational numbers. So this is just saying that K can be obtained by adjoining a root of f. So suppose that we are told, perhaps by your favorite computer algebra system, that a subring O with an explicitly given Z basis is a ring of integers of a number field. The main question that we want to solve is how can we formally prove that O is indeed equal to the ring of integers of K? So in Lean, this would mean that we have something of type subalgebra of K, so we should think of this just as being a subring of K. And we want to prove that this O is equal to the ring of integers of K. And we are assuming that we know O explicitly. Perhaps we know a Z basis of O. So two initial questions come into mind. First, how should we define O in Lean? And second, how can we compute in it? So in order to be able to solve these questions, we first need to consider efficient polynomial arithmetic. So the way polynomials are defined in MathLib, in the Lean mathematical library, is not suitable for computation. So in fact, the polynomial arithmetic is non-computable. So we will use an alternative representation of polynomials over a ring R, and we're going to represent them as lists over R. So these lists will correspond to the coefficients of the polynomial. And we have a map that goes from lists over R to the MathLib polynomials over R. And here we have the description, polynomial.offList takes as input a list over R and outputs the corresponding polynomial in MathLib. And we also define operations on lists corresponding to addition and multiplication on polynomials. So we can translate statements about addition and multiplication of polynomials into this setting of lists. And we define computable polynomials as a subtype of those lists that have no trailing zeros. And this is similar to the way polynomials are defined in MathComp, in the MathComp library for Coq. So they also use lists for defining polynomials. And we prove, or we define the isomorphism between computable polynomials over R and the MathLib polynomials over R. So now that we can compute with polynomials, let me tell you how we can define this subring O. So again, we say that we write K is just Q adjoin some root theta of a polynomial f. And suppose we have a basis omega 1 to omega n, which is given to us as a Z basis for O. So as a set, if I want to define this in Lean, I would say perhaps take the Z span of this set of omega i's. But the problem is that if I do that, then this thing is going to have type a submodule of K, a Z submodule of K. But I want it to have type a Z subalgebra of K. So we need to convince Lean that this set, the Z span of these omega i's, is actually closed under multiplication. And we can do this by writing each omega I as 1 divided by some non-zero integer d times a polynomial bi evaluated at this root. And every omega I can be written in this form. So see, if we want to prove that this set, the Z span of the omega i's, is closed under multiplication, this boils down to proving that omega I times omega j can be expressed as a linear combination of the omega k's, where the coefficients are integers. And this, in terms of polynomials, is equivalent to proving that there exists a polynomial Sij, such that this equality over polynomials holds. So in order to prove that this set is closed under multiplication, we can provide the integers aijk, the polynomials sijk, and then the proof just reduces to checking some number of polynomial identities, which we can do because we can compute with polynomials. And what we do is all this data, so these polynomials bi's, which are used to define the basis, the omega i's, the integers aijk's, and the polynomials sij, we incorporate them, we bundle them together with proofs of, for example, these polynomial identities into a structure that we call the subalgebra builder. So for example, in this number field, which we obtain by adjoining a root of this cubic polynomial, we have that this ring O given to us by a computer algebra system is the ring of integers. And we want to prove that, but first we need to construct this O. And this O is given with the z basis 1, theta, and theta squared divided by 3. So we put this data in to construct something of type subalgebra builder. We include this data as part of the fields. So for example, you can see a field called B, and this includes the polynomials bi's defining the basis. Then A includes the polynomials ai, j, k that I told you about before, and S is the polynomials sij given as lists. And the rest of the proofs are, for example, these proofs of the polynomial identities that we can just solve automatically with decidability, or some of them with reflexivity. So if we are able to construct something of this type, of type subalgebra builder, then we can obtain the corresponding subring O, which as a set is the Z span of the basis, but now with type Z subalgebra of K, which is what we wanted. And since we now have O and we have a basis for O, we can represent every element in O just as an n-tuple with integer coefficients. So in Lean, this would be something of type fin n to z. And the way to do it is we just look at the coordinates of an element with respect to the basis that we have. And if we want to compute in O, well, we see that multiplication is completely determined by the pairwise multiplication of the elements in a basis. So we can collect this information in a multiplication table. The ij entry is just going to be the vector representing the product omega I times omega j. And from something of type subalgebra builder, we actually have all the information to construct something of type times table, which is this multiplication table. So times table is this structure that bundles together a basis of a ring, a multiplication table for this ring, and a proof of correctness of this table. And we can use then the vector representation together with this multiplication table to compute inside O. So we can translate arithmetic in O to arithmetic in these vectors. And we know how to deal with them because we have a multiplication table. So now that I told you how we can define O and how we can compute in it, let me say how we can prove that something is a ring of integers of K. So again, K is a number field of degree n, and we have a subring with a Z basis of size n. So it can be proven that a ring with these characteristics must live inside the ring of integers. And the way we can compare the ring of integers and O is by looking at the index of O in OK. So this would be the cardinality of the quotient OK modulo O. And we say that for a prime P, we say that if P does not divide the index of O in OK, then O is P maximal. So you see, if O is P maximal for every prime P, then this means that the index must be equal to 1. And this means that O must be equal to OK. So the strategy that we use is we're going to prove that O, the explicitly given ring that we have, is P maximal at every prime P. And in this way, we obtain a proof that O is equal to OK. And in order to do this, we use a theorem called the Post-Sassenhaus theorem, which gives us a criterion for P maximality. What this theorem says, well, in order to tell you what this theorem says, let me just briefly say a couple of definitions. So if we have an ideal I, the multiplier ring of I is just those elements in K such that when multiplied with I, we remain inside I. And here you can see the formalized definition that we wrote in Lean, and this is in a more general context. So we are actually talking about R algebras here, where R is allowed to be a principal ideal domain. But in our case, the one that I'm talking about here, R is just equal to Z. And now the P radical is going to be the elements in O, the elements X in O, such that there is a power of X that lies inside the ideal generated by P. And this is going to be an ideal inside of O. And again, here is a general description for this more general setting, where now pi corresponds to P. And what the theorem says is that if O is equal to the multiplier ring of the P radical, then O is P maximal. So we get a computational criterion for P maximality. And we can restate this theorem as a lemma in linear algebra. So actually, we can define this map phi from O modulo PO to the endomorphisms of the P radical modulo P times the P radical. And we can prove that if the kernel of this map, which is an FP linear map, is trivial, then O is P maximal. So what we do is we define a certificate that proves the triviality of this kernel. And in this way, we are able to prove the P maximality of O. And verifying the certificate, so essentially the certificate consists of some number of elements that are mapped through this phi to some linearly independent set of endomorphisms. And to verify this certificate, it involves checking n identities in O and n identities in O modulo PO. But this is okay because we know how to multiply inside these rings. And the way we set things up makes it so that we can solve these goals automatically using, for example, decidability. And with Dedekind criterion, we can actually reduce the computation of proving P maximality for every prime P to just proving it for a finite list of primes. So what we did is we formalized some irreducibility certificates for polynomials because we needed those to convince Lean that K is a field. The maximality certificates that I described, together with the mathematics behind them, we wrote Sage math code that given an irreducible monic polynomial over the integers and an integral basis for the ring of integers, it gives you a Lean proof of O being equal to the ring of integers of K. And in this way, we were able to verify some entries of this big number theoretic database, which is the LMFDB database, for a choice of number fields, including 142 non-monogenic number fields of degree 5. And we also formalized some other computational tools, such as resultant and discriminants, which allowed us to, again, verify the discriminant of degree 3 number fields. And this is using that and using the fact that we can verify an integral basis. So this has been a case study in formal verification of number theoretic computations. Hopefully some steps towards bridging this gap between a traditional computer algebra system and a proof assistant. And the major part of the effort was not only dealing with formalizing the abstract mathematical content, but also finding suitable representations for computation. In total, we wrote 13,000 lines of code, and 32,000 lines of Lean code were automatically generated from our script to verify these entries. And some further directions for future work are perhaps optimizing these computations to deal with higher degrees. So in particular, the discriminant computations, which we were only able to do for degree 3. A tighter integration between Sage Math and Lean. So right now, you press a button, you give the irreducible polynomial, you give a basis, and you press a button, and you obtain a Lean proof of the equality, which you can then import into Lean and check. But perhaps exploring a tighter integration would be interesting. And certifying other invariants that are also relevant for applications such as class group and unit groups. And yeah, thank you very much.
Thank you, Adam. We have time for question.
Thanks a lot for this talk. So if I understand correctly, you in your computation, you're only dealing with polynomials where the degree is smaller than 8. So I would like to understand what is limiting you. Is it the computation? Where is the performance bottleneck, basically?
Right. Yeah, so in these identities that we need to verify, there is these particular ones that involve some exponentiation. So something needs to be raised to the p to the t power. This is all happening modulo p, so in principle this is fine, but still we're having some troubles with these computations for a big degree and a big prime. And we get timeout errors. And another bottleneck is in the computation of the discriminant of a number field. This requires computing determinants. And the way determinants are implemented in MATLAB, well, these are not very suitable for computation. And we haven't really tried yet to optimize these computations, but this should be doable.
Give the talk. I was wondering, can you give us some numbers on the efficiency of the different parts? So how much computation is spent in the computer algebra system, and how much time is spent for generating the Lean code, the Lean scripts, and how much time for checking within Lean?
Yeah. So generating the certificate using the computer algebra system and generating the code for these examples takes a couple of seconds at most. And this is because the discriminants of these polynomials are not too big. But this can be problematic if the discriminant is too big because it involves factoring some big integer. But right now, for these examples, only takes a couple of seconds. And then checking the proof in Lean, which is in two parts. So first, the proof of irreducibility of the polynomial, and then the actual proof of the ring of integers takes in total for degree 5, which is the one that we did the most, around 30 seconds.
I guess usually an important part optimization of ideal computations is to use Grosvenor bases. Do you use them at all? Do you compute your own in Lean? Do you rely on Sage to provide the basis for you?
For this particular project, we don't need Grosvenor bases. So yeah, Grosvenor bases will come into play when we're dealing with ideals in the ring of polynomials. But right now, everything has a Z basis. So we can do everything with linear algebra.
Okay, thanks, Alan, for the talk. And congratulations for this distinguished paper award.
Thank you. Thank you.
So now we have a 30 minutes break, and we are back at 11.
the second session of the day. First up, I'm going to introduce Daniel Zakon, who is going to be talking about split decisions, explicit context for substructural languages.
Thank you very much, and thank you everyone for coming. I'm going to be presenting our paper Split Decisions, Explicit Context for Substructural Languages. This is joint work with Chutasano, Alberto Migliano, and Brigitte Pientka. So before I begin, I will just give a quick overview of what I mean by substructural systems. So specifically, I mean those systems or languages which in some way omit or restrict the standard structural rules of weakening, contraction, and exchange. So weakening, if something is derivable, it remains derivable when adding assumptions. Contraction, we can collapse identical assumptions. And exchange, we can reorder assumptions arbitrarily. Some substructural logics, probably the best known is linear logic, which omits weakening contraction while allowing them in some form through what's called an exponential modality. And it lends itself to a natural interpretation of resource usage, where we can read a linear sequence as stating that every one of the assumptions is used precisely once to produce a proof of the consequent. And there are some other systems. So strict, also known as relevant or relevance, logics omit weakening and amount to using assumptions at least once, affine at most once, and so on. So given the natural interpretation of these substructural logics to resource sensitivity, it's no surprise that they have been used in a variety of applications as type systems for resource for systems where computational resources of some form are important. So variables, data, memory, and so on. So there's applications in memory management, quantum computing, concurrent programming, and so on. Now, in the realm of programming languages, formal proofs about meta theory ensure that our formal systems behave as intended. And insofar as traditional pen and paper proofs are tedious and prone to error, formal verification of meta theory by proof assistants minimizes human error and thereby establishes trust in them by rigorously checking that there are no mistakes or overlooked cases. Now, the trade-off of mechanization techniques for structural languages is fairly well understood since the introduction of POPL' in 2005. Both the PL and mechanization communities have invested a great deal of effort in understanding the trade-offs of different techniques. But in substructural settings, where often seemingly minor extensions to systems can compromise basic safety properties, which makes the need for verification even greater, in my opinion, the trade-offs of different mechanization techniques are not yet well understood. And while there are quite a large number of mechanizations of structural languages, especially linear ones, their design is usually for specific use cases without concern for reusability. And recently, the concurrent calculi formalization benchmark was introduced, calling on the community to develop best practices for mechanizing concurrent systems, the first challenge of which focuses on the difficulties that arise when mechanizing linear ones. So it is in this context that we introduce CARV, which stands for Context as Resource Vectors, a general infrastructure for mechanizing substructural languages, which we argue is general enough for formalizing substructural systems in all their many flavors. And it is implemented in Beluga and used for a wide range of case studies. And in this talk, I'll give a high-level, code-free overview of this infrastructure and how it can be used in practice. So first, let's look at an example of a substructural system. So here is the implicational fragment of the linear sequent calculus. I'll omit variables and proof terms just for simplicity here. So the axiom rule states that we can use the resource A to produce a proof of A, leaving no leftover assumptions. Cut allows us to compose two proofs, one providing A, another one using it. The linear implication left rule, or lolly left rule, says that using A lolly B means that if we can show a proof of A, then this warrants a proof of B. And finally, the linear implication right rule states that proving A lolly B means using A to produce a proof of B. So from a mechanization standpoint, what are some of the considerations here? Let's look at the lolly left rule as an example. So if we read it in a bottom-up manner, we have some general context of assumptions. We check that A lolly B appears somewhere in it. Exchange is being assumed implicitly. It's not necessarily at the top of the context. We remove it from that context. And then what remains is split into two disjoint contexts, delta 1 and delta 2. Now, when we mechanize such a system, all of these operations have to be made explicit. What does it mean to use up this resource? What does it mean to split? Or if we read it top down, what does it mean to merge? So there are various approaches in the literature to context modeling and splits in particular. And the prevailing approach is the naive and perhaps the most intuitive one, which is to explicitly rip apart contexts. And this has the benefit of lending itself to encodings that are very close and often identical to their on-paper formulations. A downside is the high overhead of technical lemmas that need to be proven before even getting to the system, to proving the interesting properties of the system in question. And it's also, in general, incompatible with standard name-free representations of binars, so de Bruijn indices, de Bruijn levels, right? Because since the context is being explicitly ripped apart, references to locations within a context become no longer relevant as things are moved around. And also, as well, simultaneous substitution for the same reason. What would be nice would be to instead encode our substructural systems directly within a substructural logical framework. So for instance, LLF or SELF. And this would avoid the need for explicit context altogether. And then factoring out for the user the overhead of resource management, like splits. The glaring downside is that there are very few implementations. I think, in fact, only SELF has an implementation, and none of them have any support for verifying meta theory yet. And finally, there are alternate approaches which aim to sidestep the need for explicit context splits. So for instance, linearity predicates, where instead of enforcing, say, say linearity with how contexts are models, we enforce it as a predicate on the syntax of expressions while keeping the context intuitionistic. Leftover typing is based on the idea that, say, linear terms leave leftovers when they consume resources, which are then fed to another term. And these approaches have, as I said, they eliminate the overhead of explicit context splits. But they often are quite different from the on-paper formulations of the languages in question. And they can be difficult to extend to more exotic substructural systems. So in particular, ordered systems, which restrict exchange. It's not obvious how to use linearity predicates, say, in such a system. So the technique that we develop aims to maintain the intuitiveness of explicit context and explicit context splits while being flexible enough to accommodate various binding styles, including de Bruijn, and also be amenable to simultaneous substitution. And then general enough to be highly reusable across a variety of applications, not just in the linear case. And this infrastructure we call Carve. And the key idea is based on the work of Anders Nielsen and Sherman, where assumptions persist as contexts are manipulated. What do I mean by that? So here is an example. Informally, if we read this proof tree bottom up, we start with a general context which has two assumptions in it, A and A lolly B. We remove A lolly B. We use it up, which we denote by changing the color from black to gray. And then what remains is split. There's only one element that remains, specifically the assumption A. It is assigned to the left branch of the tree, and to the right it is shaded out. And then a new assumption B is added to the top. So this idea, right, and then as we can see, we can keep de Bruijn indices because it's still meaningful what indices refer to, right? And in practice, we capture this shaded idea with tags. So we annotate assumptions with tags indicating resource availability. And these will be elements of some algebraic structure which can be used to capture the substructurality, the notion of substructurality in question. And then we can parameterize the context merge operation by the given algebra, which is equipped with some operation. So more concretely, let's look at an example. The this partial commutative monoid L will characterize allocation for linear affine contexts. So an assumption with the tag 0 is one that is no longer relevant in this branch of the derivation, or it is used up, or it never was relevant, while one that is given the multiplicity 1 is one that is linear. So it must be used before the proof can terminate. Or if it's affine, then it has already been used, it must be used at most once. So an example of a context, if we look at the one on the left, we have A is given the tag 0. When we split the context, both branches are assigned 0 because of this multiplication table. When we have the second element, which is given the tag B, we have two ways of decomposing it. We can either give the left context 1 and the right one 0, or vice versa. We choose the former. And then the third element, we allocate 1 to the right and 0 to the left. Some other examples of resource algebras. For fully intuitionistic context, we can just use the trivial monoid, which amounts to not using tags at all. For graded context, we can use this numerical monoid. And a nice thing about this idea is that we can also combine resource algebras in meaningful ways, say to capture exponentials alongside linear resources. So in this example, we have linear resources, and we also have exponentials. We have ones that are available unrestrictedly, which are given the tag omega. Now, in addition to the modularity of this approach, the construction also has the advantage of allowing the underlying algebraic structure to naturally impose itself onto the merge operation. So for any context, if we take the set of contexts with the same elements up to changing the tags, then it itself will be if we're dealing with a partial monoid, then that will be a partial monoid. If in fact it is a total monoid, then the context structure will also be a monoid. If it's commutative, then the context one will be commutative, and so on. And this extends to other properties as well. So let's go back to our running example, and let's try to reformulate the cut rule. It's quite simple. So instead of having delta 1 and delta 2 in the bottom, if we read it in the bottom up, we start with an arbitrary context delta. We use our merge operation to split it into two, delta 1 and delta 2, and then we allocate one to the left and one to the right. And we'll use this double turnstile to distinguish sequence in this carve setting. What about the lolly left rule? Naively, we'd like to do the same thing. We remove a lolly b, which has the tag 1 since it is a linear assumption, and then we split what remains. The problem is, of course, is that we don't have implicit exchange, and we can't assume that a lolly b is at the top of the context. Our solution is to define a general context lookup / update operation that can be used to update the type and multiplicity of a context. And it's we read this as stating that we look up inside delta that A appears with tag alpha at position n in the context, and then delta prime is the result of changing that entry to B with the tag beta. And it's defined in, I think, the obvious way by just recursively traversing the context. And I should say, though, it's not actually needed for the running example that we've been looking at, that we include this index n1 so that the infrastructure is general enough to accommodate De Bruijn indices and other name-free styles of bindings. 2, to ensure that the operation is deterministic, because there can be repeat entries. And then 3, so that we can use our update predicate to define things like permuting context elements without having to consider a separate predicate. And this could be used, say, to prove the admissibility of exchange within a linear system. We can also define lookup in terms of this general predicate and so on. And update satisfies, I would say, all the expected algebraic properties. So it's reflexive, symmetric, transitive. It distributes over our merge operation and so on. And this is useful not only as a sanity check, but these properties can also be exploited in proofs to, I think, great effect. So let's revisit our lolly left rule. If we read the rule bottom up, we start with an arbitrary context delta. We look up that A lolly B appears with tag 1 inside the context somewhere. I omit the index n just because it's not relevant here, but we can think of it as just being there under the hood. We change the tag from 1 to 0, so it becomes no longer available linearly. And then the resulting context, delta prime, is split up into delta 1 and delta 2, and then we allocate them as we did with the cut rule. So what about the leafs of our proof trees, our axioms? Naively, again, we would like the context to be singleton in this case, but since we are updating linear things by changing their tags from 1 to 0, and also since our split is creating a lot of things potentially creating a lot of assumptions with the multiplicity 0 when we reach the leaves of our proof tree, we need something a bit more general to enforce that a context is singleton or empty. So we describe this using this exhaustedness predicate, which essentially states that all the elements of a given context are in some sense harmless, by which I mean that they are subject to some form of weakening. So in a linear case, that will mean that all assumptions have the tag 0. In more complex substructural systems, you could have other things lying around. For instance, in the joint linear unrestricted monoid we saw earlier, you could have assumptions labeled 0 and omega still lying around when you close up. So reformulating our hypothesis rule, if we read it bottom up, we start with an arbitrary context delta. We look up that A appears with the tag 1 somewhere inside the context, change the tag to 0, and then check that the resulting context is exhausted. In this case, that either it is empty or that all assumptions are given the tag 0. So our infrastructure has been fully implemented in Beluga, which is a dependently typed proof environment which supports specifying formal systems within LF and then proving properties about them. And we've used our implementation to mechanize a wide range of case studies. So we've proven meta theory about linear sequent calculus and a bidirectional linear natural reduction calculus, proving cut elimination in the first and the equivalence of those two systems. We have encoded a linear lambda calculus using HOAS and proven subreduction for it. A linear lambda calculus using De Bruijn indices and environment-based semantics. We have an affine lambda calculus also using higher order abstract syntax. And finally, we have an encoding of the session-typed process calculus CP, also using higher order abstract syntax, for which we've proven subject reduction and also equivalence with a system called structural CP, which is essentially a variant of CP that uses linearity predicates. So this amounts to essentially an adequacy proof of SCP with respect to a first order encoding of CP. Notably, some 40 to 80% of the code base devoted to mechanizing each result in terms of the number of lines are properties from the reusable common infrastructure, as summarized in this table. So in other words, much of the weight is being carried by the infrastructure, factoring out for the user a lot of the technical properties that otherwise would have to be proven separately directly. So in summary, our key contribution is the introduction of Carve, this general syntactic infrastructure for mechanizing substructural systems with resource annotations, which gives us different substructural systems in some sense for free by parametrizing contexts by a suitable algebra. And encodings very closely resemble their on-paper counterparts while still being compatible with simultaneous substitutions, different styles of bottling bindings, as well as various language-specific design choices. it also uses low-level primitives like lists, which makes it in principle compatible with just about any purpose assistant. And we have implemented our framework in Beluga alongside a wide range of case studies showing the power and versatility of our approach. Ongoing work is porting Carve to a more mainstream proof assistant, in particular Rook, formerly known as Coq, where in theory we could leverage tactics and proof automation in a more meaningful way. And also a proof using logical relations, which is, I think, is a gap in the current work, which is a class of powerful techniques which is notoriously difficult to mechanize. The follow-up to the POPL' challenge was POPL' Reloaded, which concentrated specifically on mechanizing logical relations. I should also add that none of the case studies involve restricting exchange, and that is some other future work, is using Carve to encode an order system. So thank you very much, and I look forward to your questions and comments.
All right, thank you. Plenty of time for questions.
Thanks, Tuck. That was quite loud. You use a lot of partial operations. Do you have some machinery to help you do that? Is it a pain point, or please expand?
That's a very good question. In practice, all of the operations are implemented as relations between contexts, which I would imagine in Beluga that works very well. In a system that uses LF, when porting it to, say, Coq, that would be a design decision that would have to be made whether or not you would want to keep it as an operation, given the partiality, because partiality can cause issues down the line.
Hi, I just wondered, when you do this update operation, that you replace some resource with number 1 by the same resource now with label 0. Why don't you just delete the resource immediately so that you don't have this check on being exhausted?
I think. Right, so even if we had switched to a removal operation from an update 1, we would still need the exhaustiveness check, given how context splits work, where context splits are creating assumptions with the tag 0. But the decision to update instead of removing was to keep in with this philosophy of keeping context intact. So if we had a context split, and at some point in one of the branches of the derivation, we removed an element, then that context would no longer be mergeable with all of the other ones at the same position, and they would need to be removed as well in order to keep mergeability. And so just updating it maintains the context. It makes sure that every element remains there up to tags, which works very nicely. Thank
you. In your exam, when you change these from 1 to 0, it seems like that would limit your PCM, because you started by talking about an arbitrary PCM, and then you just have this multiplication operation. But I mean, not every PCM has a 1. Your intuitionistic example only had omega, right? So does that do you have a version of this which is involving some relation, which is defining what 1 and 0 are in this context, or how would you generalize that, or why didn't you, I guess?
If I'm understanding your question correctly, so the capturing different notions of substructurality is carried fully by the choice of algebraic structure and by the typing rules. So an example is, for instance, if we switching from a linear system to an affine one, just means changing the axiom rule. Otherwise, the encoding remains identical. So instead of, we eliminate the exhaustiveness check from the leaves of the proof tree, where things that are assigned the label 1 are now allowed to exist inside. And so exhaustiveness becomes, in some sense, irrelevant. Another choice would have been to redefine exhaustiveness to include both ones and zeros, which would work which would work similarly. Does that address your question? Thank you.
This system reminds me quite a lot of Bob Atkey's QTT and other similar things with quantities in context, and also on the typing judgments themselves. Do you have any comments about this?
So it's similar in as much as it uses tags, but it's used in a very different way. Ours is to capture resource availability. If I'm not mistaken, in QTT, it's for dependent types. So the application is quite different, though there are some commonalities.
Yeah, can you say a bit more about the combinations of partial monoids that you do? Are these like sort of standard from monoid or partial monoid theory? And can you capture the kind of combinations that appear in the granular language, if you're familiar with that?
Right. So if we look, as an example of this, I give two examples over here of a way that you can combine linear and unrestricted assumptions. The first one is more in the style of a split system, like a dual intuitionistic linear logic, where linear assumptions are completely separated from ones that are unrestricted. But unlike in a dual setting, we actually don't need two separate contexts. They can all live together within one happy context, since they never actually interact. In the other one, which I don't use in any of my case studies in practice, but could in theory be used, it's slightly more complex. So for instance, if we view it as a split, an assumption given the tag omega, when it is allocated to two separate contexts, it can assign omega to both branches, but it can also assign one to one and omega to another. Or it can give one to both. So things can switch from being unrestricted to being to becoming linear. A benefit of the right one is that it is actually a monoid with unit 0. The one on the left is not. It is very, very partial.
Right. Are these what was I saying? Instances of general, like I could take any two partial monoids and one operation will give me the left thing and one operation will give me the right, or?
I think you would need to be a bit more careful in the sense that you need to look at your specific application and really consider what algebraic structure you need. It isn't necessarily just copy and paste. It really depends on the application.
I think that's all the time for questions we have. Let's thank our speaker again. Thank you so much. All right, so next up, oh, yes. Yeah, thank you.
Can you hear me? Is it okay?
Okay, great, thank you. All right, so next up we have Florent Hubert with machine-checked proofs and programs in algebraic combinatorics.
Thank you. Thank you for the organizer to allow me to talk. It's my first talk about proof in a wide conference, because I'm not at all a proof guy. I'm, let's say, computational mathematics guy. So I'm playing with algebraic combinatorics, and I've been heavily involved in computer algebra development, such as SageMath. Actually, I coordinated the development of the combinatorics library in SageMath for a few years. And during that coordination, I had the opportunity to see how not so good the implementation was in terms of correctness. So, and that's a problem, because in algebraic combinatorics, we are always dealing, we are trying to prove algebraic identities using algorithm and data structure. But when I see how bad those data structures are implemented, I'm wondering about how bad or proof are they already correct? So that's what I wanted to investigate in this work. And today, I will present a relatively large library based on rock and mathematical components. So the library which was developed under the lead of Georges Gontier to prove the four-color theorem and the order theorem. And what I'm dealing with is about symmetric identities, about symmetric polynomials and character formula for the symmetric groups. So really computational question. And my flagship result is the Littlewood-Richardson rule. And I will try to give you an idea of what is the statement of this rule and some very rough idea of how you can prove it. Okay, so what is the Littlewood-Richardson rule? It's a rule which allows to compute the product of two polynomials, which have some specific property. And it's proved by executing symbolically some algorithm on the concatenation of two words. So really, I'm going back and forth between algebraic identities, computing with polynomials, computing with concatenation of words, which is the three monoids, and executing symbolically some algorithm, which this algorithm is, you will see, is related to the longest subsequence problem. So really, I'm doing both algorithm and algebra at the same time. And to illustrate that, here is the map of my library. So what is at the bottom in brown is just support, let's say infrastructure. Blue is combinatorics. Red is algebra. And there are few side results which are not related to Littlewood-Richardson rule, which appear in green. And it's, okay, it's a few thousand lines of codes. So let's try to give you an idea of what it is about. So I consider n variable, which in the example would be A, B, C, D. And I consider polynomials in all those variables. So here is a polynomial expression. And I say that a polynomial is symmetric if it is invariant by permuting the variable. So for example, if you look at this polynomial and if you exchange A with B, then A square B will become EB square, A square C will become B square C, and AC square will become BC square, and so on. So that's two examples of symmetric polynomials. And okay, and I will define a specific basis for those polynomials. And basically, my rule is how do you compute the multiplication is this basis? So something quite elementary, let's say. But the proof is not elementary at all. To have a basis, I need some combinatorial ingredient. So the most important ingredient is the notion of integer partition, which is just you take an integer and you try to decompose it as a sum without taking care of the order. So this is a decomposition of 12. This is another decomposition. And actually, there are lots of decomposition, 77. And we call that a partition. So since the order is not important, we sort them decreasingly. And there is a notion for the sum and the length of a partition. And for reasons which will appear later, we love to draw partition by box diagram. So this is the partition 5, 3, 2, 2, which is a partition of 12. So this is a diagram with 12 boxes. which are arranged 5 boxes, 3 boxes, 2 boxes, 2 boxes. And I'm using the French convention. Usually the English draw those diagrams upside down, if you're familiar with those. Okay, let's talk a little bit about formalization. I want to formalize this notion, and I'm following the idea of small-scale reflection. I will comment about that later, which means that when I'm giving a combinatorial definition, when I can do that, I'm giving a predicate which computes the definition, which answer true or false, because I will comment about that. And then, using this reflect statement, I'm giving some statement which is equivalent in this case, which means that the last element of the partition is not 0, and the partition is decreasing. The nth element of the eth element of SH is larger than the eth plus 1. Okay? So that is integer partition. And that's my main object, so please don't try to read the definition. So that's a definition which is due to Cauchy and Jacobi. I define a polynomial by the quotient of 2 determinants. Since determinants are anti-symmetric, the quotient is something which is symmetric, and it appears that the quotient is not a rational function, but an actual polynomial. Here is an example. Okay? And this basis is extremely important. So the first claim is that this is a linear basis of symmetric polynomials. Any symmetric polynomials is a linear combination of those polynomials. And since this is a basis, it makes sense to compute the product in this basis, which means if I have 2 such Schur functions, I can decompose their product in Schur function, and there are some coefficients. And it happens that those coefficients are integer, positive integer, which is very important from the combinatorial point of view. If they are positive integer, they are counting something. And that's my point. There is a small comment which, okay, let me skip that. It's not at all very important. So if we look at the history of the Littlewood-Richardson rule, the statement was in 34, and it was the first wrong proof. And actually, it was also the first wrong example. Even the example they give in the paper was wrong. They claim that some coefficient was, if I remember correctly, 22, and it was actually 24. They missed two elements in their enumeration. And I don't know, maybe 6 or 7 wrong proofs were published before Schützenberger came with the first proof in 77. And all those proofs were published, accepted, and everyone was convinced that the result was proved. Okay? And yes, there is this funny comment by Gordon James, which says that the Littlewood-Richardson rule helped to get men on the moon, but was not proven until after they got there. I'm not sure it really helped to go to the moon, but it's a rule which is really pervasive in mathematics and even in science. So here is a sample of application of this rule. The first comment is that computing Littlewood-Richardson coefficient is something which is sharp P complete. So if you're not familiar with sharp P, is the counting version of NP. When you have an NP problem, you're supposed to answer yes or no. With a sharp P problem, you answer an integer. But that's the same idea. So which means that modulo something like P equals to NP, there is no better way to compute those numbers than enumerating the solution of a combinatorial problem. Okay? Because of that, it's appears in Murmulé geometric complexity theory. And okay, I'm not reading all the application. It's just to convince you that those are very, very fundamental numbers, and they even appears in quantum physics or chemistry. So, okay. So how do you compute those numbers? So I need this notion of Young tableau. So this is a partition. This is 753. And I want to fill the box with letters. And the rule is that it should be weakly increasing along rows and strictly increasing along columns. Okay, and there is this notion of row reading, which is the natural reading of the shape. I don't know, sorry, it's in the bottom of the screen for those which are. So I'm just reading the boxes in their natural orders, and that gives me a word, okay? So this is the formal definition of a Young tableau. Again, I'm giving it as a Boolean predicate. And actually, I'm first giving a definition of dominate, which means, is it allowed to put two rows on top of each other? And then if I have a sequence of rows which is ordered by domination, this is a tableau. Okay, this is my definition. And let me redefine in a totally different manner those sure functions, which were the quotient of the determinant. So now I'm taking a partition. Those are my variables. And I'm computing all the way to get a tableau with A, B, and C with this shape. So there are 8 ways. And now, for each ways, I'm just counting how many A, how many B, how many C. This gives me a monomial, and I gather that in a sum. And you can see that there are 2 possible tableaus of this shape. And so there is a coefficient 2. It's not at all obvious from this definition that those polynomials are symmetric. But they are. Actually, they are the same as the one I previously defined, but I only will prove that at the end using a specific case of the Littlewood-Richardson rule. Okay, so that's the definition. Maybe, sorry for those which are at the back, but so I'm defining a sigma type for tableaus of a certain shape, and this is, I'm giving it a mathematical component structure of a finite type, which means I'm really giving to Coq a way to enumerate all the solution. And then in this definition, I'm defining just a multivariate polynomial by the sum of all tableaus of the product of et cetera, just a translation of whatever. So this is there is a technical condition. I don't want to give you this definition if I'm asked. Okay, so that's how you compute the Littlewood-Richardson coefficient. So you have 2 partitions, which is the 2 polynomials you're trying to multiply, and one at the top, which is the result. Because of degree property, it's the sum of what is at the bottom must be equal than the sum at what is at the top. I'm multiplying polynomials, so degree should add normally. And here is the rule. So this partition is the outer shape. So here I have 5 boxes, 4 boxes, 3 boxes, 2 boxes. And this is the inner shape. So I just cut 3 boxes, 3 boxes, 1 box. And now I want to fill this, respecting the tableau condition, so increasing in rows, increasing in columns, with 4 zeros, 2, 1, and 1, 2. And there is this extra condition, which is Yamanouchi, which roughly means that if you read the thing backward, at each steps you have more 0 than 1, than 2, than 3, than 4. So it's kind of complicated intertwined condition. And so those are 3 examples. And actually, because polynomials are commutative, those 2, I'm just multiplying 4, 3, 1 by 4, 3, 2, 1 in one sense, in one order and in the other order. So those 2 results must be equal, but it's not at all obvious that there are as many as solution here than solution here. So there is a bijection, but it's really not obvious that those two numbers are equal from this definition. Let's keep let's skip a little of all those statements. I'm just expressing that. And then the main theorem is what is at the bottom of my screen. If I multiply sure of P1 by sure of P2, I get the sum of all partition of shape with D1 plus D2 boxes. So sorry, I should have written that D1 is the number of boxes in P1 and D2 is the number of boxes in P2. Of course, P1 must be included in P, and there is this coefficient times the Shor function. So that's my main result. And how is it proved? It's proved using the longest increasing subsequence problem. I will give a little detail here. And so there is a bijection between word and pair of tableaus. And this bijection, actually, we prove that it's computing a normal form in a quotient of the free monoid. So here is really where algorithm and algebra are linked together. We have an algorithm which computes a normal form for a monoid. And thanks to that, I execute symbolically this Robinson-Shenstead algorithm on the concatenation of two words, and I get my proof. This is the detailed outline of the proof, but I won't I won't read it because it's too technical. Let me just give a little bit about what is this increasing subsequence problem. Let's pick a word and try to get an increasing subword. So subword, you delete some letter, and you want something which is increasing. In this case, A, B, B, D. It's ending in A, B, 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 B. It's also increasing. And what I want to compute is the maximal length of such an increasing subsequence. So something quite elementary. And here is the algorithm to compute that. You start with an empty row, and you insert one by one the letter of the word in the row, following that rule, following the two rows. If there is a letter in the row which is larger than the letter you want to insert it, you take the first letter, which is larger, and replace it. If there is no such letter, you simply append your letter. So for example, if I have this tableau, A, B, C, I want to insert A, so the first letter which is larger than A is this B, and I'm just replacing it. And in this second rule, if in this word I want to insert a B, there is no letter larger than B, so I'm just appending a B. And the specification is that you can prove that the ith entry of your row is the smallest letter which ends an increasing subsequence of length E. So that proves your algorithm, and that's what is stated in formally there. Okay. Yeah. So there is a way to record. Okay. So first of all, sometimes you're replacing a letter here. And if you don't want to lose any information, then what you can do is to insert the letter in a new row which is on top, and then you get the tableau. And there is another remark, is that if you record the order in which the boxes are added, you can inverse the whole process and recover the word which you had at the beginning. So this is a bijection. Okay? And the crucial point of the proof is to use this bijection to lift the definition of sure function, which were commutative polynomials, as non-commutative polynomial. And if you have non-commutative polynomial, then you're just concatenating language. There is no multiplicities, and you only prove things using inclusion of sets. There is no multiplicity. Anyway, that's the idea of the proof, but okay. So it's time to go to some conclusion. So first, I presented everything in terms of polynomials, but there is an isometry which is due to Frobenius, which allows to translate everything which was proved in the language of polynomial in the language of character theory for the symmetry group. So I did this translation, and you have those two statements. And in particular, this means with these statements that I really have an implement a program which computes in Coq the character table of the symmetry group. So, and it's really something that we love to do when we do algebraic combinatorics, is to take some abstract computation like character and translate it in really concrete elementary objects like polynomials, like number and things like that. So that's really typical of my field of research. So conclusion for combinatorial lists. First, it's feasible, which was not at all obvious when I started that. In particular, it was my first development in Coq, so it took quite a lot of time, 6 months of my time. And it proved that Schutzenberger proof, the one which was published in '77, was correct. And not all my colleagues was convinced that this proof was correct. So now, and also for that, I get a certified implementation. So now I can compute those numbers, even in Coq itself, and get number as large as a few thousand in Coq. Okay, so that's the conclusion for, there is also a further comment for combinatorialist, but I keep it for in my second conclusion slide. So what are my conclusions? First, small scale reflection is really something which is useful when you're doing combinatorics. When you're doing combinatorics, there are lots of particular cases in your algorithm. Those are those which are false when implemented in Sage or in C. All the trivial case, the empty permutation, all the empty objects. And having the system dealing automatically with those trivial cases really help you to focus on what you want. Another comment is that, so this, for me, this is starting to be some old work, because I finished formalizing everything even before the COVID crisis. So in the meantime, mathematical component had evolved. And at that time, extending the algebraic hierarchy was very hard. And now they have a tool which is called Hierarchy Builder, which is a game changer. It's quite easier to extend the algebraic hierarchy. They still have improvement in terms of error message, but the tool works. Thanks to the mathematical components basis, formalizing algebra was relatively easy, where formalizing combinatoric was much harder. And one of the reasons I feel is that because in algebra, there are a lot of generic things you can reuse. In combinatorics, I don't see very how to reuse things. So, however, there is something which was not so helpful. So, mathematical component is very oriented toward finite things. In particular, all sets are supposed to be finite, and if you want to deal with finite set, you must be inside a finite type. So it was not so good for combinatorics. And one thing which is really striking, that's my okay. That's okay. Is that when you read the paper, there are lots of cases where the definition, the combinatorial definition, which is given in the paper, is not the one which is used in the same paper. I have lots of examples where you define something with some diagram of box with some properties, and then if you read the paper, that's not the definition which is used. And we do that every time. That doesn't help formalizing. And finally, since my goal is to extend computer algebra system, I tried to estimate what I've done. So my estimation is that I formalize 5% of what is in SageMath about symmetric function character of the symmetric group. This is, okay, you have the number. So which says that if we want to formalize all the Sage combinatorics library, we need something like 50 million of line of code, which somehow stopped my... Thank you for your attention.
Thank you very much. This is a great talk. We have time for some questions.
Surely you didn't take the number of lines of code for this and then multiply by how many things, because there would be so much overlap, right? So
more overlap in proof than in computer algebra.
For proving the things that you have in the Sage library, won't you have lots of overlap in your formalization? You'll use some lemmas in the formalization that you've already proved for other things, no?
Yeah, sure. But I mean, when you're developing a computer algebra system, if there is a function, you can also reuse. So I'm not sure.
Yes.
Yeah, thanks. So what, when you're talking about developing a computer algebra system, obviously things like SageMath are very optimized, right? So maybe, I don't, okay, not having used them. So what, okay.
We want to be expressive, but we are not so fast.
Okay,
really.
So is working in Rock, is this, do you think this is actually like scalable and could, be used as a computer algebra system, even if it's less efficient in some ways?
Yeah, I mean, that's more or less what I'm trying to do, yeah.
All right, any other last one? Actually, I think we're pretty good on time. So let's thank our speaker again. Yeah. And for our last talk, we have a virtual talk. So you can leave that there, yeah. And you can take the mic off. No. Great, and so this last talk is, I think, delivered by Nicolas Schaap, monadic interpreters for concurrent memory models.
Can I start?
Yes.
Okay, thanks. So, one of the goals of this work is to define executable semantics of for a concurrent subset of LLVM-IR. Okay, so LLVM-IR is a compiler intermediate representation that is widely used. There are many programming languages that compile down to LLVM-IR, and in turn, it compiles LLVM-IR compiles down to many different architectures. Finally, there are many program transformations and optimizations that are defined on LLVM-IR. This gives it a very central role in many compilation infrastructures, which makes it a very interesting starting point for a verified compilation infrastructure and to formalize its semantics. This is the whole point of the existing Vellum project. Vellum's goal is to efficiently model the semantics of LLVM-IR in work, formerly COC. How it does it is by using a fitting library to represent programs in work, which is the interaction trees or iTrees library. The iTree library is designed specifically with large-scale programming language semantics such as LLVM-IR in mind. Vellum is based on it, but in its current state, there is no support for concurrency in Vellum. It's limited to sequential LLVM-IR programs. And adding support for concurrency is no easy task. There is a lot of added complexity with concurrent memory accesses that can give rise to data races, for instance. And there is, in fact, a whole field of research dedicated to such concurrent memory accesses, which is called weak memory models. This is no easy task, but this is our long-term goal with this paper, which is to model the semantics of concurrent LLVM-IR in work. For that purpose, we follow the Vellum method, which is to first define, create a fitting data structure for representing concurrent programs, which we called choice trees or C trees for short, and we presented it at POPL 2 years ago. And then we get to the present paper, which is to use this new data structure to model a concurrent subset of the semantics of LLVM-IR based on C trees. Okay, so I first need to detail the basics about choice trees. So this is an infinite, or more precisely, co-inductive tree model for representing programs. It takes the form of a rock library, which takes heavy inspiration from iTrees, but with added primitives for non-determinism. Just like iTrees, it has nice properties. We can use C-trees to define modular semantics that are made from many reusable parts, and to define executable semantics that can be tested against some litmus tests, for instance. Okay, in a C-tree, there are 4 possible kinds of nodes. The simplest one is leaf nodes, return nodes, that just materialize the return of a value at the end of the execution of a program. Then we have the visible event nodes that represent an effect. They represent a request to the environment of the program with many possible outcomes, many possible answers from the environment. Then we have the unary step nodes that represent an internal computation. They are the counterpart for tau transitions in process algebra. And finally, and that's what's new in comparison with regular iTrees, we have the non-deterministic branching BR nodes that represent an invisible non-deterministic choice. Okay, so I'll explain in a bit more detail visible event nodes. So as I said, each this node represents an effect during the execution of a program. I depicted on the left an example, a small example LLVM IR program in simplified syntax, which loads a value from address A, then stores it back to address B, and finally returns 0. And I also depicted the corresponding C3 on the right. Okay, so of course, the effects that will happen during the execution of this program are memory read and memory write events. So at the root of the tree, we first have a read of A, which corresponds to the initial load. And depending on the value that is read, we take either the left or the right branch. Assuming we take the right branch, we get to the right back of value 1 to address B, and finally to the return of 0. Okay, we can go even further to make the semantics of C3, I3, or C3 appear by interpreting the visible events it contains. For that purpose, we can use stateful interpreters for some kinds. I mean, for one kind of visible nodes that appears in the tree. And I depicted an example on the left of a C tree with print events and memory access events. And we would like to interpret the memory access events starting from a state in which address A is mapped to value 1, the state being a mapping from addresses to their current values. So we start from the root of the tree, and there is a visible print event. This is not a memory access, so we leave it as is. Then we get to the visible read of A. The semantics will just be to return the relevant value from the mapping. And as I said, in our initial state, A is mapped to 1. So the right branch is the right one. And so we keep this right branch and discard the other one. We trim the tree. And the visible read node is consumed. It becomes simply a unary step node. Okay, then we reach the visible write of 1 to B. And it updates our memory state so that B is now mapped to 1. And finally, we reach the return of 0. We still return 0, but we also return the final memory state. Okay, that was for an example of I3 or C3 interpretation of a visible event. But we can go much further than this example. And in fact, we have a general methodology to make the semantics of a C3 appear, which is to successively interpret each kind of event nodes. We just did it for memory events, but we could do the same for the print events that were in the tree, or for other kinds of events. For instance, the Vellum project, which is based on I3s, applies this approach to LLVM IR, which seeks successive layers of interpretation to give the semantics to the various kinds of visible nodes that represent what can happen during the execution of an LLVM IR program. Okay, and after there is no visible event node left in a tree, we can actually execute the tree or the model that we get. Because in the end, the model that we get is a function that maps an initial state to a tree that is assuming the program terminates and is deterministic, just a sequence of unary step nodes that leads to a return of the final state of the execution. So it maps an initial state to a final step. In this way, this is execution. Okay. I've not talked until now about the meta theory of C-trees. The first thing to do to prove meta-theoreticals about C-trees is to define a fitting notion of equivalence. And the way we do it is by reusing as much as possible existing literature on label transition systems, or LTSs, because we have a systematic method from any C-tree to build an underlying LTS, and then we use existing notions of equivalence on LTSs in order to reason about C-trees. And starting from this point, our main notion of equivalence is strong bisimulation on LTSs or on C-trees. And in the way we build LTSs, we are very careful to give non-determinism semantics to the non-deterministic BR node. This is depicted below. We can see a C-tree that is translated into an LTS, and the transitions that would correspond to the non-deterministic BR nodes are kind of collapsed. But I won't delve too much into details of the meta-theory of C-trees. It's out of the scope of this paper. Rather, I'll move on to our model of LLVM-IR concurrency. So our source language is a small subset of LLVM-IR, but a subset that still retains its concurrency features with some thread management functions from the C11 standard library for thread creation and joining, and concurrent atomic memory accesses with several levels of atomicity. Okay, starting from such source programs, we can first, of course, represent them as C-trees, and then we have an interpretation stack made of several layers of interpretation to consume the various kinds of visible events in the tree until we get to a final executable model with no visible event node left. And a first interesting result on this interpretation stack is our result of transport of equivalence. Each of these layers preserves program equivalence, meaning that if we have two programs that are equivalent at this stage, after interpretation, they will still be equivalent. Okay. So I'll now go into more detail about the different passes of this stack, starting with the representation. The actual representation procedure is defined by induction on the source syntax. It's completely standard, but what's interesting is the various kinds of events that we introduce in the C-trees. There are three main kinds of events. First, variable accesses effects with reading and writing to local variables and reading from global variables because they are read-only in LLVM-IR. Then we have events to represent thread creation with a spawn event that takes an LLVM-IR function and just spawns a new task from it. And finally, memory access events with load, store, read, modify, write, and fence events, each annotated with a memory ordering level. Okay, I will skip the variable interpretation pass because it's standard, and I'll move on directly to the interpretation of multi-threading. The basic idea is that in order to model the parallel composition of n threads, each represented as C-trees, we interleave their C-trees into a single multi-threaded C-tree. And in this context, at each point of the execution of the program, we introduce a non-deterministic branching node, a BR sched node, which chooses in which thread we will next perform a step of execution. I depicted an example on the right with a yellow thread and a green thread represented as C trees, and we would like to take their parallel composition. So we have two threads, so we'll start with a scheduling sched node with two children. Assuming we want to schedule the yellow thread first, we will take the left branch and get to a load of A, which is directly taken from the left C tree. And after having performed this first step, we go back to another sched node, which will choose whether we continue executing the left C tree or move on to perform one step in the right one, and so on and so on. It gets slightly more complicated when there is a new thread that is spawned. Basically, subsequent sched nodes will have one more child to account for this additional running thread. And in practice, this is not implemented using a regular interpretation path as I showed earlier, but based on a custom co-recursive combinator that we called interleave. Okay, the next and last step is the interpretation of concurrent memory accesses. In fact, we support three alternative concurrent memory models. We support the basic sequential consistency or SC model. We also have an interpreter for the total store ordering or TSO memory model. And finally, the most interesting one, an interpreter for a subset of promising semantics. And between these different memory models, we have a few simulation results to state in particular that sequential consistency is a stronger memory model than TSO and promising. The original promising semantics is a very complete operational concurrent memory model that supports many levels of atomicity, just like LLVM-IR. This is what makes it interesting in our setting. And in our development, we support a subset of promising semantics with most levels of atomicity that it supports, but monotonic accesses are partly left to future work. I now detail why. Okay, so the basic idea behind promising semantics and the family of promising semantics is that in our state, we will associate to each memory address a timeline of all the past writes that have occurred at this memory address. I depicted, for instance, a timeline for some address A to which value V1 has been written, then V2, then V3. But in fact, it's a bit more complicated than just that, because for monotonic memory accesses in particular, they can be executed out of order. So maybe the write of V3 happened kind of before V2. I mean, it's I can't delve too much into detail, but there is some reordering that happens with some sanity checks, of course. But in the end, this allows to have load and store reorderings. This is supported in promising semantics, and this is supported in our partial implementation too. But it gets more complicated for load store reorderings. The actual original promising semantics supports load store reorderings using what they call promises, which is a kind of speculative memory write. At any point of the execution, a thread can promise that at some point in the future, it will write some value to some address. And this forces us to maintain an invariant that at any point of the execution, all the promises can still be fulfilled by their respective threads, no matter what happens in the other threads, in order in particular to prevent the out of thin air problem. But this is quite complicated, and this does not play well in our setting, in our very operational setting. This would be quite complicated to represent. We would basically have to carry proof terms in our C-trees. So we do not support right now load store reorderings in our development. But if we can keep in mind that our long-term goal is to have a verified compilation infrastructure, this is not that big of a problem. Okay, so we finally get to the executable model once we have interpreted every kind of visible event. But unlike the example I've shown in the beginning, there is still some branching in our final tree because there is still some non-determinism. We have to schedule the remaining non-determinism in the final C tree. We have several schedulers that we wrote in work for that purpose in order to schedule the remaining branching sched nodes. We have a round-robin scheduler and a pseudo-random scheduler. And in order to choose a promising timestamp when a read or write occurs, we have two schedulers, one that always chooses a maximal timestamp, which basically gives us a sequentially consistent execution, and one that chooses a random, pseudo-random timestamp, valid timestamp. Okay, there is an alternative for executing our final C trees, which is that instead of choosing one branch when there is some non-determinism, we could just explore all the branches and collect all the possible end results of the execution. For that purpose, we wrote a collecting interpreter in OCaml, thanks to Rock's extraction feature. And for a small LLVMIR program, such as the one on the left, it will output the possible final values of the execution. This is very useful to compare different memory models on small litmus tests, but of course, it does not scale very well to large programs. Okay, so in this paper, we defined modular semantics for concurrency in work with pluggable memory models, thanks to our use of C-trees, and we applied this to the subset of LLVMIR concurrency. Our code is available on GitHub, but this is still in early development. There is still a lot of things to do. For instance, we could prove much more results, many more results on the interpretation stack. In particular, it would be nice to have results of reordering between the different interpretation passes, saying that we could swap the orders of different interpretation passes and get the same semantics at the end. And of course, in the long term, it would be nice to merge our effort into the actual Vellum project. Okay, thank you for your attention.
Thank you very much. Okay, so we have a few minutes for questions.
Hello. Yeah, thanks for the talk. So one thing I was wondering is you said you're inserting these sched nodes in a whole bunch of places. Do you have any way to be sure that you added enough of them? Like, is there a theorem you can state, or maybe even you have proven that this is like equivalent to interleaving semantics with the per thread small step reduction or anything like that?
In fact, how the co-recursive combinator is written is that it introduces sched nodes between I mean, after each step in the label transition system. We are sure that the granularity is enough because we insert them whenever something happens in a thread.
Where in the pipeline does this happen? Because like if you do this too early, then the individual events might still be very big, and then you don't get interleavings. Again, still don't get enough interleavings, right? Like it depends on the granularity of your events.
The idea is that it happens at the beginning, but we still interpret the variable access events before because they are thread local. There is no interaction between threads when you consider register, reading, or writing. But the idea is that it happens at the beginning.
Okay, thanks.
I have a question because I'm doing weak memory models too, and I was thinking about how to apply your stuff to what I'm doing. And one thing I'm wondering is that when you do interleaving, I mean, when you represent parallelism as deterministic interleaving, you assume implicitly that all your load and store events are atomic, logically atomic in some sense. And in the I3/C3 framework, I was always wondering, is there a way as an intermediary step to actually represent those two things happen in parallel without fixing the order first?
The visible loads and store and so on events happen in some order, but their semantics can be such that it captures out of order semantics. As I've shown, we can model a large part of promising semantics, for instance. But of course, it would be possible to have more granularity by having more atomic memory access events at the perhaps micro-architectural level if we consider specific architectures. And we could introduce, in this case, sched nodes between micro-architectural steps if we had more granular events. Yeah. But this is not exactly our research direction.
Yeah, no, I mean, if you don't want to do that lowering early and leave it to the precise memory model, I was wondering whether at the intermediary point you could actually represent a parallel composition, because here you are doing the switch from two threads to a non-deterministic interleaving relatively early in your pipeline, and that restricts what kind of models you can plug after that.
I mean, it could be the interleaving could happen after the memory access interpretation, given that we introduce some kind of yield events that is kind of like in Brooks interleaving semantics. And this is one of the past reordering results that I would like to prove, but I'm not sure it answers your question.
Yeah, I think you can take that offline. That would sounds like a really interesting discussion. But in the meantime, we have lunch next.
I just wanted to mention that we have a Discord, that there is a Discord thing for the whole conference, so you can discuss on paper. So there is already a question for Dan, the first talk after Emily's invited talk. So if the speakers can connect to Discord during the week, maybe there will be question and you can discuss over there, and it will be very nice. So you can follow the discussion over there.
Great, that's good to know. Let's thank our speaker again.
Can you hear me? Yeah, okay. Thanks. I'm going to present joint work with Doan Kim, Teppei Saito, and Akihisa Yamada. And in this talk, I will first give you an introduction to what I'm actually doing. So I'm working on certification of non-reachability in term rewriting, and I will explain all of these three words here, certification, non-reachability, and term rewriting, one after the others. So certification for me means not verifying a program, but checking that the output of untrusted tools is indeed correct. So I'm considering some unverified tools as they are participating, for instance, in the termination competition or in the confluence competition, which are given some validation task, and then they produce an answer. For instance, a given program is terminating or not, in combination with some certificate why this should be the case. And what we do is actually we try now to run this proof, which will generate this answer on the certificate, and all the reasoning that is done in the tool will be verified, formalized in some proof assistant, leading to some formalization, and this formalization is also equipped with verified algorithms to check whether these proof techniques are applied correctly. And then via code generation, we actually get a verified certifier which can check then whether the generated answers of these automated tools is correct or not, and so we can then accept or reject such a proof. In our setting, the proof assistance we are using is Isabelle HOL, and the library in which we do our formalization is the ISA4 library, the Isabelle formalization of rewriting, which at the moment mostly is about rewriting, but it also contains certain other languages. For instance, we also have a little bit of SMT solving and LLVM formalized there. So this is the framework of what we want to do. Now, what is our aim? The aim is what we generate here is the certifier that is called CETA, and we would like to support more proofs that these tools are using. So in particular, we want to be able to certify more non-reachability proofs. And what this is actually an analysis that shows that something cannot be reached in a setting like safety proving, that starting from some initial state, we cannot reach a bad state where some property might be violated. Or in the context of a compiler, certifying that a certain code fragment cannot be reached, so we don't need to okay? Or in termination analysis, this is used to actually generate a tight approximation of the call graph so that certain parts of the code don't have to be investigated for termination proving. And non-reachability, proving these non-reachability is actually part of COCO. COCO is the international confluence competition where one category in this competition is to prove non-reachability or reachability, which is also known under the name infeasibility, automatically on a set of systems. Now, this non-reachability we consider now here is in the context of term rewriting. What is term rewriting? Basically, it's a very simple model of computation where you just have, in our setting, first-order terms on the left, which rewrite to first-order terms on the right, where here, for instance, we see the three rules implementing the Ackermann function, and here we have rules which check whether a given argument is a natural number or not, where the natural numbers here are using piano notation, so zero and successor notation. And here in this talk, I will restrict to plain first-order rewrite systems. In the paper, you also find results about conditional rewrite systems, which is an extension of this formalism where you can have side conditions on the rules. Good. What is now the question of reachability? The reachability basically takes two terms, a source term and a target term, S and T. And then the question is, can we instantiate the variables in the source term and in the target term in a way that I can rewrite from the starting term to the target term in arbitrary many steps? This is an undecidable problem, and example problems might be, for instance, is it possible that from Ackermann 7,7, and then I want to check whether this is a natural number, that I can rewrite to false? In this way, this example is a very trivial one in the sense that here there are no variables occurring. So trivial task, I just have to rewrite to normal form and check what is the result. Although you don't want to rewrite Ackermann 7,7 to normal form. That would last a little bit too long. So then we can replace certain subparts by variables. For instance, instead of here having a 7, we can just write a variable here, and then the question is how to instantiate this. And the answer is again no, but now it's a little bit harder to see that this is non-reachable. Or we can even substitute both arguments of the Ackermann function by variables. And now, however, the answer is yes, because you can plug in for x the value 0, and for y you plug in true. And then by the first Ackermann rule, you rewrite the inner arguments to s of true. And then via the is-not functions, you end up in is-not of true, which yields false. Okay, so it's not always obvious whether some reachability problem is satisfied or not. Now, non-reachability in terminal writing is, as I said, a subcategory of the confluence competition, and there are various tools that try to automate these proving techniques. And for instance, the two tools, NUT and InfChecker, they actually can synthesize non-reachability proofs for the first two examples that I've shown you. And the tools InfChecker and non-reach, they actually can automatically find a reachability proof of the third example. The problem is that all of these proofs that we have here of these tools cannot be certified because the power of our certifier CETA is actually limited at the moment before this work to syntactic algorithms to check non-reachability, or to use tree automata approximations, where the tree automata is used to over-approximate the set of reachable terms and then show that this is disjoint from the target terms. Or it can also take detailed rewrite sequences for reachability. In principle, the tool here of non-reach would be trivial to certify. Unfortunately, here the non-reach tool does not output any machine-readable proof at the moment. So what we want to do now is we want to extend the formalization and the CETA certifier in a way to support non-reachability, not via tree automata or syntactic methods, but using term orders, in particular so-called co-rewrite pairs. And here there is a nice theorem of Kihisa Yamada, who showed that a given non-reachability problem is non-reachable if there is a co-rewrite pair, so a pair of relation being a strict and a non-strict one, such that on the one hand side, we have a weak decrease from all left-hand sides to the right-hand sides, meaning that this reduction sequence will turn into a greater equal, so by demanding closure under substitution and closure under context. But on the same hand, the target term is strictly larger than the source term. And putting these together, we would somehow have that S sigma is greater or equal T sigma is strictly greater than S sigma, so S sigma is greater than S sigma. And assuming irreflexivity of the order, this is a contradiction. Okay, so this is basically what the properties of a co-rewrite pair are: irreflexivity, closure under substitution, and closure of context of the weak relation. And Yamada showed not only that this is a sufficient criterion, but this is actually an if and only if. So in principle, quite a powerful method, but of course it depends on which kind, how do you synthesize these co-rewrite pairs. So what is the easy part? We started by formalizing basically this theorem where we used the existing infrastructure of the ISA4 formalization that for many years supported termination proofs. And in termination proving, there is the notion of a reduction pair, where a reduction pair is basically a more restrictive variant of a co-rewrite pair. Every reduction pair is also a co-rewrite pair. So all the reduction pairs that are available in ISA4, like polynomial interpretations, matrix interpretations, path orders such as the lexicographic path order, Knuth-Bendix order, etc., the weighted path order, they can immediately be used to prove non-reachability by this result. So this was somehow a very nice start once formalized this theorem, and then just use all these available orderings, and we can have many more non-reachability proofs. For instance, here is now a certifiable proof which proves that this is non-reachable. We just here plug in a polynomial interpretation over the natural numbers with these interpretations, and then by calculating you can check that indeed all the left-hand sides are larger than the corresponding right-hand sides, and that the target term here is strictly larger than the source term. Okay, for instance, here we see that false maps to 2, whereas is not is just the argument plus 1, so we get 1 plus this result. The Ackermann interpretation is the second argument, so we need to compute the interpretation of the 7, and since successor is just the projection to the argument and 0 is interpreted by 0, this will be the 0, so the right-hand side is the number 1 at this point. Right, so this is what we immediately get now, and how does this look like now in the certificate itself? That is actually an XML representation of such a proof, where I'm just quickly going over it. So it's quite natural, it's not easy, not hard to generate. Basically here you see each rule is spelled out in XML, and there are 7 of them. Then you have the corresponding source and target term, and then you have the infeasibility proof where you give the interpretation of all of the polynomials for the various function symbols. And this is then passed the internal structure and then later on certified that indeed this interpretation satisfies all the required properties. Now, let's go for the harder part. The harder part is we really want to have the full power of the co-rewrite pairs. And the full power of the co-rewrite pairs means we want to drop the corresponding assumption of reduction pairs that we have strong normalization of the strict order. That is somehow the key difference between the co-rewrite pair and the reduction pair. However, since the whole development of the ISA4 library was tuned towards termination proving, in all of these term orders, strong normalization was used as a standard assumption on all the orderings that were implemented there. So just the interface to communicate with the orders did not allow to specify any not strongly normalizing order at this point. And to this end, we actually had to refactor and redesign our interface for the term relations so that now you can query these orderings after one property after the other, whether the order is stable, whether it's closed under context, whether it's transitive, whether it's reflexive. So you can query all these properties one by one. And then we additionally add certain convenience functions which bundle up certain properties to say, well, is it a co-rewrite pair or is it a reduction pair? In Isabelle, this looks like this. We have a big record type, rel impl for relation, term relation implementation, where basically we have here 3 relations, a strict one, a non-strict one, and another one, which are of type, they take a rule, so a pair of terms, and give you back a corresponding Boolean result with an error message in case the constraint is not satisfied. Moreover, besides these relations itself, you can now query like flags like, is this strict ordering strongly normalizing? Is this strict ordering closed under substitution? And the ... means many more properties you can query. In a total, I think there are 23 entries in this record data type. Now what we have is, additionally to this record, we have a corresponding predicate that tells us whether this is a valid implementation, and that basically checks that what we have executable code, meaning, for instance, for polynomial interpretations, they are in general undecidable if you think of nonlinear polynomials, whether one polynomial is always greater than another one. So what we have here is implementation of sufficient criteria, executable sufficient criteria, which can ensure that a given term pair really is in the relation. And so we have things like that we have an under approximation of the actual relation, meaning that the thing that is in the corresponding record here, if that says it's okay, S and T are in relation, then indeed S and T are in the semantically defined polynomial order. And so what we have overall is we have approximations here. We have also approximations of the property. If the flag for strong normalization says it's okay, it is strongly normalizing, then you can be sure the real ordering, the semantic one, is really strongly normalizing. And on the outside, we know that if the global validity flag says I'm okay, then there are semantic versions of the relations which have the connection to the implementation version. And this validity flag might check something that actually the polynomials that you define really are polynomials over the natural numbers. If you would assign x minus 1 to something, then this validity check would claim that this is not allowed. So this was a major refactoring, and now we had to actually adjust all the term orders that are inside ISA4 to this new interface. And there, in particular, we run into problems on those parts which are transforming given orders to new orders. So, for instance, what we had before is a theorem like given a transformation like an argument filter, if we get as input a reduction pair, then the filtered orders also form a reduction pair. So if you have all the properties before, you get back all the properties afterwards. But now we had to do it much more fine-grained in the way that we had to check, well, to transfer closure under substitution for the filtered thing, you need closure under substitution, reflexivity, and transitivity before, right? And similarly, reflexivity carries over, and we had to do a much more fine-grained analysis on all of these properties. The final thing, what we actually did is, of course, now that we have the interface that supports co-rewrite pairs, we actually want to add further co-rewrite pairs which were not available before. And here, as a case study, we took 3 different co-rewrite pairs, namely polynomial interpretations where the domain of the polynomials are the non-positive integers. Where of course, this is not strongly normalizing because you can go down from -5, -6, -7, and so on. So it's not strongly normalizing, but it's still irreflexive. So it's a valid co-rewrite pair, and Yamada's work showed that for certain non-reachability proofs, reduction pairs cannot prove non-reachability, and polynomial interpretations over the non-positive integers can do it. Similarly, there is the weighted path order, which is a transformational method, and also the covariant. There is a co-WPO, which only works for co-rewrite pairs. So what we did for the polynomials, we tried to reuse the results that we had for the polynomials over the natural numbers. And what we mostly did is interpreting polynomials over the non-positive integers can be mapped onto polynomials over the naturals just by flipping all the coefficients and negating them, and then adding an outermost negation. And therefore, we can reuse all the algorithms that, for instance, ensure monotonicity or weak monotonicity of a polynomial, which we had for the natural polynomials over the natural numbers before. So there, this part could nicely be reused. For WPO and co-WPO, we mainly had problems because our original proofs sometimes used strong normalization in parts of the proofs. For instance, to show that if a property would be violated, then there would be a minimal counterexample with respect to the strongly normalizing base order, and these proofs just no longer work since now we had to drop the assumption on strong normalization. Moreover, we detected in this formalization that extension of co-rewrite of the WPO by switching from lexicographic comparisons of the arguments to multiset comparisons. This works for WPO as a reduction pair, but for co-rewrite pairs, it does no longer work out, and there is a counterexample which shows that this extension is unfortunately unsound here. In addition to the formalization, we also wrote a small prototype tool which now really produces certifiable proofs for non-reachability proofs via co-rewrite pairs, where we implemented 3 different strategies: either use polynomial interpretations over the natural numbers, over the non-positive numbers, or use the WPO configuration. In comparison, we also looked at the certifiable version of non-reach and Mocha, which are tools which were run in the recent conference competitions on non-reachability. And the results are, well, not that impressive here, because with our technique, we are clearly weaker than the existing tools. However, we are complementary to them in the sense that from these small sets of examples, we at least got 8 new problems which could not be solved by non-reach and Mocha. And of course, by adding some of the syntactic approaches and the tree automata approaches that are built into the Mocha and the non-reach tool, the combined solver could improve quite a bit here. To summarize, what we did is an Isabelle Hall formalization of co-rewrite pairs in order to certify non-reachability proofs. This involved a refactoring of the whole term relation interface. Theoretically, we figured out that co-WPO is unsound if one replaces lexicographic comparison of arguments by a multiset comparison of arguments. And experimentally, we at least figured out that so 8 new examples could be proven via term orderings. If you look into the paper, you also find proofs to show unreachability in the conditional setting, and I'm happy now to take questions.
Time for questions.
So your certifier CETA is able to check these proofs that come out, and does that mean that you're also using it in these competitions to check if the certifying rewriters actually produce a valid certificate?
Yes, yes. So CETA is used in the Confluence competition from the beginning to check the output of the proofs, and in the competition there are always 2 modes. There is the full mode where the tools may output whatever they want, and there is the certified track where indeed certifiable proofs have to be generated. And there are currently 2 different certifiers that are participating in the competition that can check parts of these proofs. So
I see, and all of the sort of formats that these tools can output, or modes of proof, shall we say, can now be verified by CETA.
Well, there are certain parts that cannot be checked. So usually it works like this, that in the certified track of the competition, the tools have to restrict to those techniques that are known to be certifiable by at least one of the certifiers. Okay, so they might have to turn out their novel technique that just had been presented somewhere, because that will not be able to be certified. So there will always be a small gap between what is certifiable and what the tools can actually do. And well, it's my job, or I try to keep up with the tools, what kind of proofs they produce. And if I see that a certain powerful technique pops up, then I might consider this worthwhile and investigate into formalizing it and integrating it.
Any other questions? I have one. I have a question about the example of Ackermann function. Is that problem is it possible to solve that problem by using other methods? For example, reachability analysis by using tree automata approximation.
At least what I saw here, I mean, I don't know. I mean, tree automata, they might also be large, and they are computationally complex. I know that here the NUT tool was actually the first who implemented co-rewrite pairs. The NUT tool solves it also with an interpretation as I've shown you. But NUT, unfortunately, does not produce certificates in the machine-readable format. And the inf checker tool, that actually uses a different approach by translating it into some first-order model, into some formula, and that is something which we definitely cannot check at the moment, but whether it is possible to use a tree automata encoding for this particular example, I don't know. The one tool, non-reach at least, that sometimes generates tree automata, that fails on this example.
Okay, thank you. Any other question?
This is maybe a bit of a wild idea, but is there any possibility of, shall we say, closing the loop where Isabelle, right, could maybe, where you may have a property, a reachability or non-reachability property that you want to prove, and then you could have a tactic within Isabelle that calls one of these one of these tools that outputs a proof that you then translate back into a proof within Isabelle?
Okay. Well, for this application, I don't know actually at the moment. What we did is at one point, we translated termination obligations of Isabelle defined functions into term-right systems, and then actually re-imported this into Isabelle itself via our certifier to check that the corresponding first-order term-right system really is terminating. And then we had a tactic which says that if the extracted term-right system terminates, then also the function is terminating that you just defined in Isabelle. So in principle, that's workable, but in practice, it was not that useful because for loading all of our theories, it takes roughly, I think, 3/4 of an hour to just compile all the theories at the moment. And you need quite some memory just to have this functionality, and therefore it didn't pay off in retrospect. So it is possible, but with limits.
Okay, let's speak again. Okay, the next speaker is, I don't know, Cass. Okay. He's talking about intrinsically correct sorting in cubical agda. If you are ready, please start.
Yeah. All right. Yeah, so welcome to my talk, Intrinsically Correct Sorting in Cubical Acta. Joint work with Vikraman Chaturi, who is also here, Julian Roth, and Niels van der Weijden. So our story begins with a paper called Sorting with Bialgebras and Distributive Laws by Hintze et al., where they analyzed the recursion behavior of some well-known sorting algorithms from the literature and find out that some pairs of sorting algorithms have a shared business logic that can be extracted in the form of a so-called distributive law. These pairs of algorithms are dual in a way that can be made mathematically precise with the notion of bialgebraic semantics due to Turi and Plotkin from their seminal paper Towards the Mathematics of Operational Semantics. And our goal was to intrinsically verify such sorting algorithms. And what do I mean by intrinsic verification? Well, an intrinsically verified program is one where its specification is interwoven with its type, and the proof that it conforms to the specification interwoven with the program. And in order to be able to do intrinsic verification, we needed to work in a dependently typed setting, in our case, ACTA. And why cubical ACTA? Well, we needed path types in order to define a multiset type, which we will see later. Our contribution, the contribution of this paper is that we managed to define intrinsically correct version of the sorting algorithms with logics given in terms of a distributive law, and do so in a setting where the correctness of the algorithm follows purely from the correctness of this small non-recursive business logic. And we get from the correctness of one business logic the correctness of two sorting algorithms because of this algorithmic duality. And the key idea is to index the data types involved, so lists and trees for tree-based sorting algorithms by the multisets of their elements. The structure of this talk is as follows. I'll begin with motivating how we can define the, is this laser? Yeah, okay. How we can define sorting as an index-preserving map. So basically a way of formulating the specification of what it is to be a sorting algorithm. Then I give a recap of the paper hints at how to motivate why we have the business logic, why the shared business logic of sorting algorithms is a distributive law, and pinpoint where we will need to intervene for an intrinsically correct version. And then I show how we go about doing that, and also introduce the data type we use for finite multisets in cubical ACTA. All right, we begin with specification of sorting. We're looking at sorting elements of a carrier set A, which is totally ordered. So one inadequate way to express the type of sorting would be as a map from list to list. But of course, there are lots of inhabitants of this type. So we might go a bit further and require that the output is a list of elements A in ascending order. But this, again, doesn't capture sorting fully, of course, because a map that would satisfy the specification, for example, would be the map that constantly returns the empty list. So we need sort of the second part of the specification of sorting, namely that the output should be a permutation of the input. We can rephrase that statement by saying that mapping lists to the multiset of their element is an operation that is invariant under sorting. And this is still an extrinsic way of expressing this property of element preservation. But we can reformulate it once more and phrase it intrinsically, naming that sorting is an index-preserving map if our data types are indexed by a finite multiset of their elements. And so the type we would write for this in ACTA would be this: if EI list is element index list, and OEI lists are ordered element index lists. And yeah, the index G here in the output is the same as the input, and that is basically element preservation. All right, I begin now of a recap of hints et al. 2012, and I'll start with the recap of the categorical semantics of structured recursion, because that's what gives rise to this definition principle of bialgebraic semantics. The relevant categorical semantics is that for recursive data types, can be described by a so-called base functor, which is essentially the data type with the recursion factored out into an extra argument. So the base functor for some common data types here, the natural numbers, would be like the maybe functor. Or for a list of element of type A, it would be 1 corresponding to the nil case, or A times X. And then the recursive data type is reconstructed from this base functor by taking the fixed point of it, which is done by consecutively applying it to itself. And the least fixed point, so in the category of sets, gives us inductive data types, whereas the greatest fixed point of this base functor gives co-inductive types, which are non-necessarily well-founded trees of shape given by the base functor f. So for the co-inductive data type for the list base functor would be lists or streams, so possibly non-terminating lists. Now I continue with bialgebraic semantics. Namely, this is a definition principle that arises in the case where we want to define maps from a recursive data type into a different recursive data type. And I say recursive here and not yet inductive or co-inductive, as you will see shortly, because yeah, this basically gives us two different ways we could do it. Namely, we could treat the input data type as inductive, and then we could define such a map by induction, given an algebra for the base functor of the input. Or we could define it co-inductively by giving a co-algebra for the base functor of the output. And a way that gives us both is by algebraic semantics, where our business logic is now not an algebra or a co-algebra, but a distributive law. And I won't say what that is precisely, but I will illustrate by showing an example of the simplest sorting algorithm defined in Hinze et al., which is the bialgebraic sorting algorithm insertion bubble sort. Yeah, we have first we have the list base functor, and so we said sorting should go from lists to ordered lists. And so in the original 2012 paper, right, they're verifying it, so they have an ordered list base functor, but this is just an alias for the normal list functor. And the shared business logic of insertion sort and bubble sort is given by this so-called distributive law. Again, I won't go into the details of why this corresponds to these algorithms, but suffice it to be said that this is logic, and then the recursion is added back in by using folds and unfolds. Right, so this is what we're starting out with, and we want to define an intrinsically correct variant of a sorting algorithm that should also have a business logic of this form. I will pinpoint now why the type here is not sufficiently expressive to guarantee that sorting is correct. Obviously, one error we could make is not correct in inversion. So here, B is smaller than A, but nothing in the type prevents me from just leaving those in order. Another mistake I could make is I could discard elements, or I could duplicate one of the elements, and this would violate element preservation. And then a third issue, and this I've sort of swept under the rug until now by talking about the recursive data types, which are only really a notion in a category where the carriers of inductive and co-inductive data types coincide. And that is that bialgebraic semantics necessarily makes use of unfolds. And an unfold for any arbitrary co-algebra could produce potentially infinite data. But we know that sorting gets a finite list as input and therefore should return a finite list as output. So somehow we need to have unfold operations that get co-algebras that are known to terminate. All right, so now I will go about the intrinsically correct version of the types in question. And as we just saw, the business logic is at the level of base functors. So that means that we need to encode all the properties we're interested in, so element and orderedness also at the level of the base functor. And I will also show how indexing by the finite multiset of elements guarantees that unfolds of the co-algebras in questions will always terminate. So now I begin with the data type that we use for finite multisets. This is quite relevant to the rest of the formalization and also the reason why we're using cubical agda. Namely, this is so-called quotient inductive types, where in addition to the normal point constructors, so here nil and cons, we have path constructors, which allow us to construct the equalities of this type. And so this data type models basically a quotient type of lists up to permutations of their elements. And this com constructor, which at first sight looks to allow only swapping elements at the head of a list, but composition and congruence allows us to identify all lists that are syntactic permutations. Yeah. And so on the next slide, I will show how we will index, how we'll define base functors for indexed lists and the ordered element indexed list. And so I introduced these synonyms to disambiguate the nil and cons constructors of this finite multiset type from those of the base functors, since ACTA normally allows constructor overloading. Okay, so I have rewritten here the list base functor that we saw earlier, but left some suggestive blanks, which will be filled in with the index information akin to the Connor McBride's ornaments idea, a data type and sort of adding information to it. And the information we add is this finite multiset index. So it gets added as an index parameter at the type level, and then we see the empty base case that can be indexed by the empty multiset. And in the cons case, we add the element const onto the list, onto the finite multiset index of the recursive position. So this is how we encode element indexing at the level of base functors. We can encode orderedness for the ordered list base functors by simply requiring an extra argument, which is that the element to be const onto a list be smaller than all the elements in the multiset index of the recursive position. And that would give us lists if you iterate that. All right. So now we have the base functors in place. The third problem that I pointed out in the recap is how do we ensure that co-algebras for the base functor are actually well-founded, so they will only produce finite output if they are unfolded. And I will show this on the basis of the L base functor, since the orderedness is not relevant, only the element indexing is relevant for this termination argument. Yeah, so the type of the unfold operation is the following. We have a higher order function that gets a co-algebra for the L base functor as an argument, and returns a map from a seed type to a list. And this works by a repeated iteration of this co-algebra, applying it to the intermediate seed values that are produced. And the way that termination that will be showed is by using the fact that this co-algebra is indexed. It's also an index. So the index of the seed value and the value of the L base functor that is produced are going to be equal. And so what I'm using here is ACTA's with abstraction. What this allows is for a given function, I can refine earlier arguments to the function definition by pattern matching on an application. So I apply grow to the seed value, and then I know that if I'm outputting the empty list, because of element indexing, I know that the element index of my original seed must have been the empty multiset. And if I output the cons case, so an element to be output and a new seed, which is indexed by multiset G prime, then the original multiset index G must have been equal to X multiset cons this G prime, so the new multiset index. And this is what I get by index preservation. And this means that the multiset index acts as a termination argument. So you can think about this index seed like a seed for such a co-algebra being indexed by the finite multisets of all elements that will eventually be output by iterating this co-algebra. And with every step, if I output an element, then that index decreases. So by that argument, we know that unfold of any L co-algebra will produce only finite output. So there's a small problem. So if I just write this definition like this in ACTA, it won't accept it as terminating. And this is because if you do syntactic termination checking based on these redundant patterns, these dot patterns as they're called, in cubical ACTA, then you can prove falsity. This is because of path constructors. So you can't just do this for any higher inductive type. But we can easily remedy that by defining this map by using well-founded induction of finite multiset. Yeah, and this length is just defined by using the universal property of the finite multiset as a free commutative monoid. So there's a implementation detail, and we also mentioned some more details in the paper which are relevant to working with higher inductive types. All right, so now with the data types in place, we can revisit the original the distributive law, but now in the index setting where we have intrinsically verified it. And as you can see, at the type level, we know that we have index preservation. And we had added this additional argument to the cons constructor of O, where we need to provide a proof that the element to be cons is smaller. So you can see we provide that as an extra argument. And then in the final line, you can see there's this subst thing. And this is because, so we've corrected an inversion, but that means that out of the box, the multiset index is going to have the elements swapped. So the order in the elements has been changed. So we need to substitute along the path constructor com, which allows exchanging the elements, to convince ACTA that the finite multiset index has remained the same up to this path equality. So this is another technical detail. You might wonder, okay, what does the term like an index data type, a data type indexed by a higher inductive type, substituted along one of the path constructors of this higher inductive type, what does it evaluate to? And this evaluates to a sort of semi-stuck term, or a normal form, basically. The way that data types indexed by higher inductive types are implemented is due to Cavallo and Harper. Yeah, you get these normal forms which are of the form transp something. So you can't necessarily do something with that, but then you can just forget the index information and map this back to a normal list. And by doing that, you will just get an algorithm. All right. Now to conclude. So what were we able to do? Well, by indexing by this finite multiset, we achieved three things in one go. We encoded the element preservation property. We encoded orderedness by using the all predicate transformer. And this multiset index also acted as a termination measure for the unfolds of coalgebras for the ordered list base functor. And the intrinsically correct algorithms we get as folds or unfolds are correct solely by virtue of the intrinsic correctness of the distributive law. So we have basically localized the proof obligations to a non-recursive thing that the algorithm does, which could be argued to be its essence. For more algorithms, so we also verified the other algorithms from the original Hinze 2012 paper, which are quick / tree sort and bottom-up / top-down heap sort. This is basically routine once you have figured out how to do things in this index setting. And we also outline a categorical semantics of what we're doing. Namely, we work in the slice category set over multisets, finite multisets. And for those, I refer to the paper. Finally, future work. So this is something I'm actively looking into as well, is I'm interested in conditions under which we have these coalgebras in an index setting which are all well-founded. Another question would be, are there more algorithms, more interesting algorithms whose business logic can be expressed at the level of a distributive law that we could verify in a similar manner? All right, that was my talk.
Time for questions.
In the final slide with the code, where you describe the substitution thing, is there any reason to define the tourist to not preserve the index? I mean, instead of defining year list G, you use list A. Is it? Yeah.
Yeah, I mean, basically, throwing away the index is how you get it to look like something recognizable. Like, if you, like, you can keep the index as long as you're working in this index setting. But afterwards, if you want to continue using it, like in the rest of your program, then you have to forget about the index. So that's the only reason why you would do that.
My question would be, would you think that it's possible to also verify the complexity of the sorting algorithms in this setting intrinsically?
That's a good question. So basically this multi-set index, right, it kind of acts as a step counter in a way. So in the original paper by Hinz et al., they do note about the complexity that, like, for these, like, the naive sorting algorithms defined in this way, you get like the quadratic complexity, and there's kind of a sort of hand wave reasoning, like it's not verified, but I think it might be possible. Basically, structured recursion like limits the way in which you can define things, right? So in that sense, it might be possible to do that. I'm not aware of a framework where you can do that exactly. I know there's some work about like about using step indexing, and so, but I think those complexity proofs, they're usually done in some framework where you sort of have these you do the step indexing outside of the algorithm, sort of in your meta language. Whereas here, this multi-set index kind of, it exists in our object language, right? We're dealing with it in the code of the program itself. So I'm not sure exactly how it would translate, but it might be possible that you could use this also for the complexity. So then you would do three things in one go. Complexity and termination, they would go hand in hand. But yeah, that's a good suggestion. That could be possible.
It's not clear to me, what do you use the truncation argument in the multi-set definition? It never shows up in the slide after. Could you remove it, or?
This is defined by eliminating from the finite multiset, and you use the fact that it is a homotopy set. You eliminate into the homotopy set of propositions, and so I think it's necessary for that definition, and also for the length that we also defined by the universal property. One thing, yeah.
The length you could define it directly with a fixed point, or?
Yeah, the length you could define just by pattern matching and recursion, but the predicate, that's the one where you really need to use the universal property, and there I think you can't do it. So yeah.
We can take one more question. Any other question? Then let's thank the speaker again. Next speaker is Christina Kark, and she is talking about formalizing simultaneous critical pairs for conference.
So.
Yeah, this does work. So yeah, I'm Christina. I'm a PhD student at the University of Innsbruck. And together with my supervisor, Art Middeldorp, I work on formalizing confluence criteria in Isabelle. So this is going to be another Isabelle talk and another term rewriting talk. We already had one of those today. So the outline of my talk is going to be that I will first introduce term rewriting just using an example similar to what you saw from René earlier. And I'll explain what confluence is in this setting. Then I'll describe the confluence criterion that we formalized, which is based on simultaneous critical pairs, or SCPs for short. Then I'll present some of the proof ingredients that we used for the formalization, but I won't explain the full proof in detail because I think this is way too technical for a talk like this. And finally, I want to give some insights that I gained from working with Isabelle on a rather complex project like this, and then there will be a conclusion. So let's start with term rewriting. So I have another example. You already saw something similar with the Ackermann function. And now it's just, yeah, it doesn't compute anything specific. It's just a very useful example for the things I'm going to show you later. So this is a term rewrite system consisting of 3 rules, and I just gave them names, alpha, beta, gamma, to easily refer to the individual rules. Then you can perform rewriting doing single steps like this, or what I is so-called multi-steps, where you combine, where you perform multiple single steps simultaneously. So for example, in this multi-step here, we do the 2 applications of rule beta at the same time to rewrite the G of A to G of B. And a more interesting multi-step would be this, where we apply all 3 rules at the same time, and then you get the term on the right. And multi-steps are always denoted by this arrow with the circle in the middle. What you can do with multi-steps, you can rewrite as long as there's no overlap in your, as long as no rule rewrites a function, so long as no 2 rules rewrite a function symbol at the same time. So as long as there's no conflict, basically, you can perform steps simultaneously by a multi-step. And term rewriting in Isabelle has a long tradition at the University of Innsbruck. As you already heard before, we have this big library called ISA4, the Isabelle formalization of rewriting, and that's been actively developed for at least 15 years. So I think it's actually a bit longer, but the first publication was in 2009. So what is confluence? That's one of the most interesting properties of term rewrite systems, and we also have this big competition every year, this confluence competition, where tools compete trying to prove as many systems confluent as possible. And formally, this is a property where you want to show, so this property guarantees that if you have 2 rewrite sequences starting, then you can join back again to the same term. So if first you diverge in 2 different directions, then it must be possible to converge. And this is a very nice property because it guarantees, for example, unique normal forms of a term rewrite system. But this is undecidable. Like most interesting properties, it's undecidable in general. But there are many criteria and many criteria that apply to certain classes of term rewrite systems. And many of those are based on critical pairs. And also the one that we formalized is based on critical pairs, to be precise, on simultaneous critical pairs. So to give you an idea of these critical pairs, let's look at our example again. So what we do for critical pairs, we look for function symbols which appear in the left-hand sides of more than one rule. So in this example, we would have the function symbol G, which appears in alpha and in beta. And then we try to find a kind of minimal instance of a term which can be rewritten with both of these rules. So in this example, if you take f of g of a and y, so the term here at the top, you can rewrite it with either beta or alpha. And the way such a minimal instance of a term is constructed is by doing unification on the left-hand sides of the rewrite rules. So you would do unification and then instantiate the variable x appearing in the rule alpha with the a, and that's how you get to this starting term. Now the whole thing, so this thing consisting of the 3 terms is called a critical peak, and just taking the 2 terms at the bottom, that's called a critical pair, just to get the terminology right. Now these confluence criteria are usually enforce certain conditions on the way such a critical pair must be connected by rewrite steps. And in this example, you could go from left to right by a single step, applying rule alpha again. And just to give you an idea, this is the formal definition of a critical pair. We don't have to go into detail here, so I think the example says more. But yeah, this is what you would need to formalize in Isabelle, and what is formalized, what has been formalized for a while, actually. One thing I want to point out, one thing that's really annoying in the formalization is that you have to first rename the variables appearing in the rules to make sure that you don't have the same variable names, which would lead to conflicts in the unification. And that's something that's a bit annoying in the proofs because you have to carry this renaming around with you all the time, kind of. Right, so let's look at the criterion that we formalized. This is due to Ukui, who published it in 1998. And it says that if you have a left linear term rewrite system, so that's one where the left-hand sides of the rewrite rules are linear terms, so they don't contain duplicate variables. So if you have such a left linear rewrite system and you compute all the simultaneous critical pairs, and then check that they can be joined by a sequence like that, where you have a arbitrary rewrite sequence coming from the left and a multi-step coming from the right. So if all of the simultaneous critical pairs fulfill the condition, then your rewrite system is confluent. And I have an example where this is actually applicable. And this example is taken from this database, which is used for the confluence competition. I adapted it a little bit because it was actually a longer example, but that's not necessary for our case. This is enough. So what you would do, you compute all the simultaneous critical pairs. And I didn't tell you what a simultaneous critical pair is yet. So let's go back once again to that slide. Here we have, for a normal critical pair, there's a single step going out from this originating term. In a simultaneous critical pair, it's allowed to have a multi-step on one side. So you have a multi-step on one side and a single step on the other side. For our example, there's actually just one function symbol. The function symbol f appears in both alpha and beta. So that's the only case where we have overlap. And that leads to so this would first be a normal critical pair, the one I drew here below. And actually, this is also the only simultaneous critical pair. So this is the only normal critical pair, and it's at the same time a simultaneous critical pair. So that's what we need to check in this case. And we need to check that the condition is fulfilled. So we take a look at how this can be joined. And it turns out that a multi-step from the left and a multi-step from the right is enough to join this. And what we need to do is we need to rewrite the two f's here using rule beta. And we need to rewrite all the k's that appear here using rule gamma. And that can be done at the same time. So this can be done by a multi-step from the left and a multi-step from the right. And then we actually also need to consider the symmetric version of that critical pair. But yeah, it of course holds the same way. So actually, Okui's criterion is applicable to this term rewrite system. And what's interesting about this is that none of the other critical pair criteria that had been formalized before were applicable to this term rewrite system because they all had stricter conditions for the joinability here at the bottom. Okay, so now I'm going to introduce some of the proof ingredients that we used in Isabelle. First of all, we have all these multi-steps, and we needed a concise way to represent these multi-steps And the way we did this was by using proof terms for term rewriting. And that's a concept that we already used 2 years ago for another formalization which used multi-steps. And the idea is that each multi-step can be represented as a first-order term. And a first-order term that consists not only of function symbols and variables, like what you're used to, but also rule symbols. But the rule symbols look like function symbols then, and they act like function symbols. So what I mean by this is the labels we gave to the rewrite rules earlier, the alpha, beta, and gamma, are now used as rule symbols. And when I said they act like function symbols, it means that they can take arguments, just like function symbols. And the number of arguments is the number of variables that appear in the left-hand side of a rule. So we have, for example, alpha has 2 variables, the x and the y. So the rule symbol alpha has 2 arguments. And the arguments are exactly the terms with which the x and y have been instantiated, so the a and the g of b. And the rule beta, for example, has no variables, so beta acts as a constant. And then the more interesting examples are the 2, so those were the single steps, and then for the 2 multi-steps, the corresponding proof terms would look like this. And as I already mentioned, we have successfully applied this already 2 years ago to another formalization project, which was development closed critical pairs, which also used a lot of multi-steps. Right. Then one of the operations that we used a lot in a proof is the so-called join operation, which acts on 2 proof terms. So it's a binary operation on proof terms. And here the idea is that we want to have a way to combine 2 proof terms into a single proof term. And this can only be done if all the steps can actually be performed simultaneously. So this is a partial operation, which sometimes is undefined. Again, we just look at an example. I don't want to explain the full definition. So here we have 3 proof terms, and now let's look first at the join of A and B. So here the idea is that since the A, so the gamma here affects the A here, and this is okay, so this can be combined, and the combination then just looks like this. And if you want to know how this works in the definition, that would be the final case of the definition that has been applied to obtain this result. And then an example of when this is undefined is on the right. So if you try to combine the proof terms A and C, then the problem is that this function symbol A, which is affected by gamma in proof term A, is also affected by beta in proof term C, and they cannot both act on A. So in this case, the result is undefined. Okay, so this normal join operation like this was already part of the formalization we did 2 years ago. But what is new now is this extension to an arbitrary number of proof terms. So before that, we only did the binary join operation, but now for the simultaneous critical pair criterion, we also needed an arbitrary number of proof terms that can be joined. And the extension, I think, is quite natural. So yeah, that's just a definition in mathematical notation here. And for example, so you just start joining your proof terms from right to left. So in the example, you first join B and C, and then the result is joined with A again. And I think this looks easy in mathematical notation, but in Isabelle it was not quite that easy because join is a partial operation, as I mentioned before. So at each intermediate step, you have to kind of unpack your partial result and then continue your computation. So it was a bit, it doesn't look as nice in Isabelle as it does on paper, I would say. And yeah, so this is only defined for this orthogonal is just an expression to say that your proof terms don't have overlap. So it's defined for orthogonal proof terms. And a lot of the times when we prove some properties of this join operation, we need to first prove that in this specific case, we do have orthogonal proof terms before we can continue proving the actual property. So it just adds another layer of complexity. And what is quite nice about this operation, I think, is it has some nice mathematical properties, like it's associative, it's commutative, and there's the source operation on proof terms, which I didn't really explain here, but this is the identity for this join operation. So whenever you join a proof term with its source, then you just get your proof term again. And this makes this join operation a partial abelian monoid, which I think is quite neat. And I proved all of that. So this is formalized. The property that it's associative, commutative, and source is the identity are formalized properties in Isabelle. Then another proof ingredient are regex patterns. So this is a quite common concept in term rewriting, but we extended it to proof terms. And our goal was just we needed a way to collect all the rule symbols and the positions in the original term where the rule symbol is applied. And so we came up with these clauses, which are quite straightforward and which compute this. And we'll just look at an example here. So what we want to get is, so for this proof term, for example, we wanted to get the positions where all of these rules are applied, and the positions work like this. So this is the syntax tree of the source term of this proof term. So if you look at the origin of this proof term, that's basically the term here on the right. And then you see that alpha is applied at the root, gamma is applied at position 1, 1 here on the A, and beta is applied at position 2. And that's just what we get as a set. And this is used to compute. So what we actually want is to extract, given two proof terms A and B, we want to extract a proof term which contains every regex in A that does have overlap with B. And we need that for the definition of simultaneous critical pairs, actually, which I will show you now. So as I said before, the idea is to have a multi-step on one side and a single step on the other. And we just define both of them as a proof term. So we say that on the left-hand side, we have an arbitrary number of steps, but at least one. On the right-hand side, we want exactly one step. And the overlap, everything from the first proof term needs to overlap with the second proof term. That's also a condition in the definition. Then one of the steps needs to be a root step. So here we assume that the P's are sorted in ascending order, and then either the Q from the B step or the first P must be a root step. And then as for normal critical pairs, we have this unification problem. But now it looks a lot more complex because we don't have just two left-hand sides which get unified, but we have an arbitrary number on one side and a single one on the right-hand side, and those all have to be unified. And that's why this looks a lot more complex. And also the fact that we don't know if the root step is on the left or on the right requires us to introduce this strange intermediate term L. So this just has the, this just was introduced to deal with this kind of awkward case distinction. So yeah, that's that. And finally, the final two conditions ensure that the terms we obtain by applying the MGU, which we obtained in step 6, actually lead to the two proof terms A and B. So basically, 7 and 8 have the purpose of connecting the tau from step 6 with our original two proof terms A and B. So that's just a definition. And the original definition, which was given by Okui in his paper, used some inductive definition, which I think wasn't so nice for formalizing, so that's why it looks like this now. Working directly on proof terms, which also makes it easier for us to formalize. Right. Yeah, in Isabelle, it looks like that. Right, and also unification was one ingredient for which we needed some additional results, but I think I won't explain that in detail. It's just, the idea was that since we are dealing with linear terms, because I said we are dealing with left linear rewrite systems, so all the left-hand sides are linear terms, the unification problem has a specific shape and is actually rather easy to solve, and it can be done by this tau operation, which I defined at the top. So that's another ingredient that was used. What I think is more interesting for you as an audience is probably what did I learn from doing this complex project in Isabelle. And one problem that I faced was how do I find and use existing results, because we had this huge library in ISA 4 with lots of existing stuff, and I want to reuse as much as I can. And for that, Isabelle's freedom search is the perfect answer, especially looking for operations and lemmas by type pattern was useful for me. And then, of course, Sledgehammer is an awesome tool. Without Sledgehammer, I could never have done this. So Sledgehammer can automate part of your proofs by using SAT and SMT solvers and applying heuristics to select the correct lemmas. Another problem that I faced was how to keep track of preconditions, because some results do depend on certain preconditions on the variables and others don't. So I had several different kinds of preconditions, and the solution to that is just put them into locales, which are named reusable context, and then you can whenever I need some precondition, I just go into that locale and add my result there. So that was also quite nice. And then the final feature that I used was the HTML representation, which is also quite nice. Isabelle provides you with this HTML output, which you can then upload on some website and share with your colleagues, or share, for example, in a conference setting like this. I simply provide a link in my paper to the HTML representation, and then everybody can look at it without having to install Isabelle. Right, so now we come to the conclusion. So what we did was formalize more results on proof terms like this n-fold join operation and regex patterns. We formalized simultaneous critical pairs in general, so the definition, and then Okui's criterion, which uses them. Unfortunately, it doesn't yet work with CETA, so René already explained this connection between ISA 4 and CETA. So the goal is actually to be able to certify a tool output which uses Okui's criterion. But that's not possible yet because we need a way to compute all the simultaneous critical pairs inside Isabelle. So we need an algorithm which is verified, and we don't have that yet. So it's not executable at the moment. But instead, to make sure that what we did kind of makes sense, we proved, so we did actually formalize this connection between Okui's criterion and development closeness, that Okui subsumes development closeness. And what's also coming now, so if you want to use proof terms representing multi-steps in your own work, an AFP entry is almost finished, so in the next few months, this should be part of the official archive of formal proofs, so everybody should be able to use it. Right, that's it.
Time for questions.
Hi. So after your development of the proof of development closeness, you added the criterion of almost development closeness. Do you think there is also almost Okui criterion, or doesn't it make sense in this setup?
I think it does not make sense. So the point of the almost extension, la da da. So let's look at the definition of critical pair, if possible. So the idea for the almost extension was we treat critical pairs which have two root steps differently. And for Okui, I think it doesn't make sense because this is already, so the condition that you have an arbitrary step from the left and a multi-step from the right already gives you a lot of freedom. And I don't think you could extend that for root steps. And then you also need to consider the symmetric version all the time. And I just don't think that extension is possible here.
Any other questions? I have a question. How much complicated is Okui's proof?
Okay, so in our paper we have so we outline the proof in mathematical notation in our paper. And there it's a 10-step plan. So when I tried to come up with this in my research, I was overwhelmed by the whole thing. So I tried to split it up in small digestible steps, and I came up with this 10-point plan. And in the paper, I think it takes up 3 pages. And in Isabel lines of code, it's, I think, 6,000 lines of code. So one proof, but it's lots of small proofs, and then at the bottom, the big thing.
That's very interesting.
What's the difference between that transitive closure and the circuit step?
So the transitive closure is just arbitrary many steps, and the circle thing is when you do steps simultaneously. And as I tried to explain with the example, you can do steps simultaneously as long as the function symbol is not affected by 2 rules at the same time. And the star, so the arrow star, would allow a function symbol to first be affected by one rule and then by another rule, and the circle thing not.
I see. Thank you.
Any other questions? Okay, then let's thank the speaker. This is end of the session, and we have coffee break.
Louis Chong, and what is it about? Formalized Borrow's Wheeler transform. Just need the slides, and then we're ready to go.
Hello? All good? Cool. Hi, everyone. I'm Louis, and so today I'm going to present our work on formalized Borrow's Wheeler transform. So a big thank you to my supervisors, Alistair and Christine, who helped me complete this project. So the structure of this talk will be as follows. First, some just general motivation of why did we want to formalize this transformation? And then just a very brief overview of what the actual contributions of the paper, of what we actually did in the paper. And then a more in-depth dive into what the BW is and sort of how is it formalized. And then some just key properties about it which are necessary to understand its inverse transformation and a little bit of its formalization. And then just some concluding remarks. So without further ado, the motivation. So the motivation of this was, I thought the Borrow's Wheeler transform is a very cool transformation. But to convince other people to actually want me to do this project, the reason is that the Borrow's Wheeler transform is this invertible data transformation that what tends to permute sequences so that they have long runs where there's only just a few distinct symbols. In addition, has a one-to-one correspondence with the suffix array, which is a data structure that is very useful when we're talking about pattern search applications. And so because of these two, it is widely used in data compression and also text search. Maybe you might have heard of some of these examples, maybe not, but here's one such example, which is bzip2, which is one of the standard file compression softwares on most computers. And essentially what it uses the BWT for is as a, basically a one phase to boost the compressibility of the data. Another tool, which is a bit more domain specific, is a tool called Bowtie2, which is a genome sequencing tool, which is widely used in medical research and diagnosis. For this particular tool, the Borrow's Wheeler transform is used to transform a DNA sequence so that it can be both compressed and searched at the same time. Now, these are just a few examples, but there's plenty more. And also, there's a lot of literature about using the Borrow's Wheeler transform and analyzing it. And so because of this, it's quite important that we have efficient and correct ways to actually compute it. But if we want to be able to actually do that properly, we probably need to have a deep understanding of how does it actually work, which leads on to why we actually, or what we actually did. So, considering that I'm here speaking to you today at a conference about certified programs and proofs, naturally that means, or most likely, formalization. And in this case, what we did was formalize two different approaches to construct the Borrow's Wheeler transform. The first being its canonical construction, which is how it is described in its original paper, and also an alternative construction using suffix arrays, which allows it to actually have a linear time construction time, because what you can have is a linear time suffix array construction algorithm, and then from the suffix array, build the Borrow's Wheeler transform in linear time. So with those two constructions, naturally you want to prove equivalence, that is that they both produce the same result. And then building on this, we then want to prove key properties about the BWT so that we can actually then verify that it is invertible. And in this case, what we do is actually verify a linear time inverse, which, although albeit it does use some pre-computed data structures, but they themselves can be also computed in linear time, so not affecting the time complexity there at all. Now, all of this is formalized in Isabelle, and as far as we are aware, it is the first formalization in a theorem prover. So that's what we did in the paper, and so now a bit more on actual Borers-Wheeler transforms. I haven't really gone into detail about it. So the way that I'll explain it is through an example. Consider a sequence, yada yada dollar, where the dollar symbol just marks the end of the sequence and is treated as the smallest symbol in the alphabet. We sometimes also call it the sentinel. And the reason why we need to do this for sequences which we pass to the Borers-Wheeler transform is that we need that symbol so that we can actually do to invert the result. But more on that later. So given such a sequence, how do we actually construct the Borers-Wheeler transform? Well, what we do is first, we generate all of its rotations. And in this case, there are 9 distinct rotations. The exact ordering of these doesn't really matter because in the next step, what we do is actually sort these in dictionary order or lexicographical order. And so we end up with this, so recalling that the dollar is treated as the smallest symbol, and hence that's going to be our first rotation, and so on from there. And then the last step is to take the last column. And this last column is the Borers-Wheeler transform, and we only need this to get back to the original sequence. And what you can see is that it does tend to group some similar symbols together. Now, this is a very contrived example, very small, and doesn't really show what the Borers-Wheeler transform is actually capable of. So here's a slightly larger example. Consider the abstract to our paper, which is standard human text. Then you pass it through the Borers-Wheeler transform, and you get something which no one can read. But what you can see is that it has grouped similar symbols together. So for example, you can see all the capital W's are grouped together, and then in some lines you can just see like a whole like section on N's, and then maybe T's and so on. And because you get this type of output, it naturally means that it's very nice for data compression, especially because this is invertible. So we can get back the original. So that's sort of the Borers-Wheeler transform at a high level. And that's what this sort of high-level algorithm basically says. And to convert this into something like Isabelle, which in this presentation I'm not actually going to show any Isabelle code, but sort of like a more mathematical stylized version of it. What we do is model sequences as lists, and so we then can use Isabelle's inbuilt list functions such as rotate to rotate lists, sort to sort them, although we do have to instantiate the ordering with lexicographical ordering, and also last to just take the last element for the list. Now, strictly speaking, our definition, we purposely make it total so that we don't run into all those other issues because of it being a partial function. But when we actually do proofs about its correctness and other properties, we do need to pass around a predicate which just says that it's terminated by this special sentinel symbol. And that's what the valid thing is for. So that's the canonical construction as how it is presented in the original paper, and as shown in many sort of, if you're learning about this transformation, that's how it's normally presented. Now, moving on, you can also construct it using an alternative approach using suffix arrays. And to see how that comes about, let's go back to the earlier example and consider the sorted rotations matrix of that sequence yada yada dollar. Now, if we ignore everything after the dollar symbol, what you can see is that we have the suffixes of yada yada dollar. And not only that, these are all in sorted order, which naturally leads to the suffix array. Now, strictly speaking, the suffix array is only the thing on the left, which is just the suffixes in sorted order, but they are represented by their locations into the original sequence. So using that plus the original sequence, one can obtain that sort of rotations matrix, which then mean that you can obtain that last column, which is the Borrows-Wheeler transform. Now, we don't actually need to compute that whole rotations matrix. We can just use a function like this, which simply uses the suffix array to find that last column. And to do that, you simply subtract 1 from it and look up what the value is there in the original sequence. Because the idea is that the last column is simply represents the symbol that occurs before that suffix. Now, there is one edge case, which is when we're talking about the suffix array value when it's equal to 0, which is basically the 0 suffix, because in that case, it's the whole sequence. And so when we look at the sort of rotation matrix, that's not going to be the last column is not going to be the symbol before, but simply just the last symbol in the actual sequence, as is shown in that piecewise function. So that's how you would construct it using suffix arrays. In our formalization, what we do is something a little bit different, which still achieves the same result. So the first thing is that we actually build on some previous work where we formalized a linear time suffix array construction algorithm, but we don't actually use any of that part, but simply the axiomatic characterization of what a suffix array construction does. And that's that SA part in that definition. And what we do then is also, instead of using that piecewise function, we use modular arithmetic. Now, for those who are a little bit more eagle eye, you can see that we have to add an additional value, which is the length, so that we don't run into this issue because we are dealing here with natural numbers where you have 0 minus 1, which can lead to problems. So we add the length value before we do that so that we don't ever run into that issue. And that's the construction using suffix arrays. Now, it's sort of, are these equivalent? And this is quite straightforward because essentially what we do is show that suffixes are just prefixes of rotations, and they have the same lexicographical ordering. And because of this, the construction using suffix arrays will actually construct that sort of rotations matrix, but implicitly. And so you show that since both of them construct the sort of rotations matrix, they both will actually extract that last column, which is the Borrows-Wheeler transform. And so that's the forward direction of the Borrows-Wheeler transform. Now, onto some key properties that we need in order to talk about index. So to do that, we'll go back to that sort of rotations matrix. I know it's starting to get a little bit more repetitive at this point, but we'll spice it up here right now. So what we do now is augment it with augment each symbol with its location in the original sequence. And that's sort of to make each symbol sort of unique. Then we also want to ignore basically the center part of that matrix. So only consider the first column and the last column. And with that, we can start talking about the key properties. The first one is fairly simple, which is the first column is just the last column. Now, this follows simply because the first column is the first symbol in the sorted rotation matrix, so that has to be all in sorted order. And the other thing is that each column is a permutation of the original sequence. And so that's why this property holds. The next one kind of relates back to that whole suffix array construction, which is that the ith value in the last column precedes the ith value in the first column, except for that one special case. So in this case, you can see that y0, which is in the last column in that fourth row, should precede a1, which is in the first column. And the final property is that the relative order of equal value symbols is the same in the first column, the last column. So for example, if we just consider all the A's, what you can see is that we have this ordering A7, A5, A1, A3 in both the first and last column. Now, the interesting thing about this is that if we know the position of where one of these is in the last column, we can easily obtain its position in the first column. So for example, if we know that A5 is the second A in the last column, we can figure out that it must also be the second A in the first column. The other thing is that we know the general region where the A should lie because they're all in sorted order. And because of this, we can find out its location. And we call this the LF mapping because it maps the item from the last column to the first column. So just a bit more for this property about why it's actually true. Consider the suffixes starting with A. Now, the ordering in the sorted rotation matrix does not depend on the first symbol, as these are all equal, but rather on their suffixes. And since these must be in sorted order, they will be have that same ordering in the matrix, which then means that the A's will have that same ordering in the last column. And essentially, for all those properties, we use those sorts of arguments, except instead of using the annotations of the locations in the original sequence, we actually talk about suffixes instead, because there's a one-to-one correspondence there instead. And that's a lot easier to deal with. Anyway, moving on. Now we have all the ingredients to actually be able to talk about the inverse. So again, consider the sequence ADY, YD, AA, $, which I think most of you will have realized this is just the Borrows-Wheeler transform of yada yada $. But how do we actually invert this? Well, we can use the first property to actually obtain that first column simply by sorting it. Now, you can do this using a linear time. For constant size alphabets, you can use something like counting sort, and this is then in linear time. Then we reconstruct the original sequence in reverse order, starting at that one unique symbol that we know, which is that sentinel, which is, in this case, $. And so starting from there, we can then apply the LF mapping, or just simply go to the first position in that first column, because we know that's going to be this most simple, but doesn't matter which one you choose. So we use the LF mapping, and then we can use property 2 to find the preceding symbol in the last column, which is A7. And then we do the same, where we apply the LF mapping to find where that A7 occurs in the first column, and find its preceding symbol, which is D6. And we essentially just keep repeating this until we have a sequence that is either of the same length as the BWT transform sequence, or until we reach back at that sentinel. And that's the inverse. Now, in terms of how do you actually write that in terms of an algorithm, that's what it looks like. I'm not going to go into detail about it. But essentially, when we formalize this, we sort of split it up into three key parts. The first being that LF mapping, the second being that repeated application of that LF mapping and finding of the preceding symbol. And the last part is just basically a wrapper so that we can start at the unique last symbol. And also only do the repeated application n times, where n is the length of the original sequence, or the BWT transform sequence. With that, naturally we want to show that this actually. And so we have a very simple theorem to prove, which is if you have a sequence and you transform it with the BWT, and then you apply its inverse, you should get back the original. And the way that we prove this is first we prove that the LF mapping is correct. And so essentially that argument boils down to showing that the ith symbol is the ith symbol in the ith symbol in the last column is the ith symbol in the first column. But specifically what we do is actually say that using the indexes and talking about the suffixes, if you look at the suffixes starting with those letters in the last column, and then looking at the suffixes as they are in the first column, you'll see that their relative orders will be the same. And because of that, then it follows that the symbols also are matching there. Then the next part is to actually prove that applying this iteratively and using the second property to find the preceding symbol actually produces the sequence, the original sequence. In this case, what we actually do is prove stuff about the indexes of the symbols, so their locations, how they map, where they map to, essentially. And so what we try to show is that if you apply this sort of inverse permutation on the locations to the permutation you would obtain if you applied BWT, what you should get is this subsequence from 0 up to n, which could be rotated. And then once you have that, you can then show that if you start at that unique last symbol, then you also apply the correct number of times, you should get the sequence from 0 up to n, and from this you then obtain that you've got actually the inverse. Now to actually prove all of this, what we did was actually split up the proof into sort of two parts. We proved that all this is correct for some abstract version where we say abstract, meaning that it has additional information about the original sequence and the suffix array. And so that just makes life a lot easier so that we can actually use additional properties about suffix arrays and actually know what the exact values are. Then we do a refinement to actually eliminate all of that information so that now you only have reference to the BWT transform sequence. And then you get the proof. And so, in conclusion, what we did was formalize two different BWT constructions and prove that they actually do produce the same result. And then we formalize some key properties about that sort of rotations matrix, which are necessary for the correctness of its inverse. And then finally, we verified the inverse itself. So some future work that we are interested in looking at is a formal complexity analysis, because at the beginning I mentioned, okay, these are all linear time, it's great, but we don't actually go and formalize that linear time argument, which is something which is quite important, and it's probably good to have a look at. The other thing is that all these are implemented in Isabelle itself. And so if we want to actually have an implementation that is efficient, we actually want to either extract it to something like LLVM or even more efficient sort of SML or something like that, or even potentially even better is to actually go from do an implementation itself in, say, C or something, and then to verify that it is correct with respect to what we've proven here. So basically show that it refines our Isabelle embedding. And hopefully, it's as competitive as with actual real-world applications. And the final thing is that in the inverse, we did use some auxiliary data structures which are also supposedly constructible in linear time. Show that they are actually, that is indeed the case. Now, these are also very useful because they can also be used in other applications with the BWT. For example, you can actually use these to use the BWT as a text index so that you can actually search over it, like as if you were searching using the suffix array, for example. And that's it. So.
Okay, are there any questions? Okay.
Hi, thanks for the nice talk. So I just wondered, you require that your sequences are valid in the sense that they have this unique sentinel. Usually texts don't have this property. So what do you propose to treat arbitrary text? Use some option type or maybe type?
So for most texts, or if you consider stuff, for example, like C strings, they already have the null character. But in a lot of applications, they'll actually put their own sort of marker there. Or alternatively, they'll actually have an index just pointing to where you should begin your inverse. Now, we haven't shown that you can actually do the index version, so that might be a good thing to actually look at. And the other thing is that sometimes you might actually concatenate different texts together so that they have their own unique sort of sentinel, so to speak. And so that's why you can sort of have this sort of sentinel idea, because then it sort of makes things sort of as a marker for, not really for when you want to invert it, but then say, for example, if you want to just search the compressed text, that's probably more useful that way.
Thank you for the thank you for the awesome talk. I'd like to ask whether there is a property about your motivation. I mean, you may use in the motivation. You said that this transformation is interesting because it puts the same characters together. Is there any probabilistic property, formal property about that kind of statement, or like it's just the observation?
Yeah, good question. So ideally, we would like to formalize something like that, but to do that, you'd having to introduce information theory, so Shannon entropy theory, and then start talking about what kind of inputs you're receiving. And as far as I'm aware, I'm not sure if Isabelle has that already formalized. If not, maybe they do, then that's something to look at. If not, then I guess we'd probably have to start from the ground up and start formalizing that whole entropy theory, information theory sort of stuff. But yes, that is probably a nice thing to actually build on this. Yes, so there are some papers which they do some analysis where if you talk about, I don't want to go into too technical, but then if you given certain types of inputs, it will have a certain characterization which you can then prove properties about how much it will compress.
Maybe a very quick last question.
Yeah.
it's more a comment than a question. The question was asked, what do you do with this dollar sign at the end? Actually, there is a variant of the Burrows-Wheeler transform where you don't need it, use it using Linden World. And do you think it would be worthwhile to implement? Or?
Yes, that's something which I hope to eventually get to. But then unfortunately my PhD is ending, so maybe in my free time I'll get to do it, or maybe if I do get a postdoc, maybe there. But yes, that's certainly something to have a look at, especially now that a lot of new research in compression actually is now starting to use the bijective version of the BWT.
All right, great. Let's thank the speaker. Thank you. And we have a remote talk next, so hopefully that will work. It's actually a pre-recorded talk, so I think, I don't know if the speaker is actually online as well, but if not, I think you can ask questions. Is the speaker online? Do we know that? Okay.
My name is Agnisham. Today I am going to present my work on verified matching for regular expressions with lookaround. This is joint work with Konstantinos Mamouras and Angela Lee. Textbook regular expressions consist of union, concatenation, and clean iteration. However, in practice with tools such as PCRE or grep, there are a number of additional features available to the user. Examples include counting, which would make the regular expression more succinct, or back references, which might add some form of non-regularity. Today we are going to talk about lookarounds, which provide a way to do contextual matching. Let's consider an example. We are interested in extracting the area code from a US phone number, which happens to be the first 3 digits of it. The expression here extracts the first digits, but the lookaround also makes sure that the entire string is formatted correctly as a phone number. Lookarounds also appear in other kinds of common regexes. For example, the beginning or end of string markers are a form of lookaround, which checks that there is no additional part of the string in front of or behind the current position. Word boundaries are also lookarounds, which check that the position being matched is at the end of the word. Here we describe the contextual matching semantics using for lookaround expressions with lookarounds. The expression on the screen denotes the window from I to J being matched by the expression R on the word W. Lookarounds form windows of 0 width at a specific location. To match positive or negative lookaheads, the window spanning the current location to the end is taken into consideration. To match lookbehinds, the window from the beginning of the string to the current position is used. We use an inductive predicate to encode the semantics of matching for expressions with lookarounds. Working with negative lookarounds is slightly more difficult. The obvious solution here is to encode a construction which accepts a proof of the negation, but this is not accepted by Coq due to strict positivity requirements. Our solution is to use 2 parallel predicates, one denoting matching and another denoting not matching. Later in the theory, we show that one is the negation of another. With the help of our semantics, we can perform some simple equational reasoning. This requires 2 definitions. The notion of regex equivalence says that 2 regexes match exactly the same windows on exactly the same words. The other notion of inclusion says that the first one matches a window on a word, then so does the second one. With this framework, we can verify that just like the classical regular expressions, expressions with lookarounds also satisfy the Kleene axioms. This involves checking the semi-ring axioms on the structure formed by concatenation and union. In addition, we also have to verify certain laws involving Kleene iteration. We have also verified some properties specifically about the lookarounds. First, we can show some simple algebraic properties such as the commutativity and idempotence of concatenation of them, or their distributivity over union. In some cases, we are able to flatten the lookarounds. Another observation is that the lookarounds can be shortened by intersecting the predicates that they use. This transformation could be repeatedly used in order to remove lookarounds of bounded width. Let us take a brief look at the landscape of regular expression matching. A common approach is to use a backtracking based matcher. These can be exponentially slow on the worst case input. For example, for this expression and this input, the engine would have to explore all possible choices across all unions before finding the correct combination of them. Backtracking based parsers are used by engines like PCRE2 or grep. They are also packaged with a large number of regular expression libraries with programming languages such as Java or JavaScript or Python. The other approach is to compile the regex into a finite state machine. The advantage of this approach is that they can be simulated in linear time. And this is used by regex engines like Google's RE2 or Intel's Hyperscan. However, this approach is less flexible. On the other hand, it is easy to add features such as back references or lookarounds into backtracking parsers. In the work that we present, we have produced a formally verified regular expression matcher which supports lookarounds. It is efficient in the sense that the time required to match is linear in terms of the size of the regex and the input. Let us illustrate the matching algorithm with the help of an example. Let us consider this regular expression. It has a top level look ahead. Inside this look ahead, there is a nested look behind. Our algorithm decomposes the regular expression into multiple layers, one layer for each lookaround. At the very bottom layer, we have the expression R0. This expression is looking for the presence of a C in the past. Above this layer, we have the expression R1, and notice that this contains an Oracle query marked as Q0. This refers to the fact that the sub-expression has already been separated as R0. Since this is a look ahead, the regex must be matched on the future of the current position. Finally, we have the top level expression R hat, which has the Oracle query Q1. Consider the word ABCDE. For the look behinds, we are interested in the question, does the window from 0 to the current position match? And for look aheads, we are interested in the question, does the window from the current position to the end of the string match? First, we start with R0, and this is something which can be matched using the string itself, using usual automata theoretic techniques. And then we match R1. R1 has the Oracle query Q0, and whenever this Oracle query arises, we use the information that was computed while matching R0 to resolve these Oracle queries. Then we match R hat, and doing so requires the information which was produced while matching R1 in the same way. Let us summarize this algorithm. The main idea is to decompose this expression into layers. Each layer represents a level of a lookaround. This decomposition produces regexes with Oracle queries. We are going to call them oregexes for short. When the upper layers are matched, they may use information from the layers below. Thus, we need the string package together with Oracle valuations. We call this data structure an O string. Thus, the main workhorse of the algorithm involves matching O regexes on O strings. And we do this in a layer-wise manner, starting from the bottom, using information from the previous layers to resolve the Oracle queries. For the layers with look behinds, we wish to know for each I if the window from 0 to I matches, and this is done with a simple linear scan. For the layers with the look behinds, we wish to know if the window from the current position to the end of the string can be matched. It is possible to obtain this information using a single linear scan. This involves scanning the reversed regex on the reversed word. The correctness of our algorithm can be formally expressed by making the connection between expressions with lookarounds and O regexes more explicit. Given an expression with lookarounds, we consider the top level lookaround it consists of. Here we have the subexpression n. We have a string on which we intend to match the lookaround expression. By replacing the maximum lookarounds with Oracle queries, we obtain an O-regex. This O-regex must be matched on an O string. This consists of the original string packaged together with Oracle valuations. These Oracle valuations indicate whether the window from the current position to the end would be a match for the subexpression n. O strings are strings with Oracle valuations. These valuations comprise a list of booleans. Each boolean corresponds to the result of a maximal lookaround. It is useful to visualize O strings as alternating Oracle valuations and letters. Since each letter is surrounded by Oracle valuation on both sides, this means that there is always one more Oracle valuation than the number of letters in an O string. The concatenation of O strings is defined only if the Oracle valuations at the end of the first word and the beginning of the second word agree. In the example shown, beta n must be the same as the valuation gamma naught in order for the concatenation to be defined. This is a difficulty in Coq. So to avoid this, we instead of defining concatenation, we define slicing. Instead of writing let x equals u concat v, we would say that u and v are produced by slicing x at a certain point. Instead of lookaround expressions, O-regexes contain Oracle queries, which we denote using the notation qi. Recall that each valuation is a list of booleans. The Oracle query qi tests that the ith entry of the current valuation is true. Note that the concatenation of O-regexes correspond to the concatenation of O strings. Therefore, when we have concatenation of two queries, they behave like a conjunction. Here we illustrate how O-regexes behave with the help of some examples. For these examples, let us say that we are dealing with a scenario where each valuation consists of two boolean values. The single character regex A or B corresponds to an O string containing the letter A or B. There is no restriction on the Oracle valuations that they are surrounded by. Let's consider the regexes Q1 and Q2. These will be satisfied by O-regexes of length 0. That is to say that these O-regexes contain no letters but a single valuation. The query Q1 or Q2 assert that either the first or the second entry in this valuation must be true. Consider the regex A, Q2, B. Here the valuation between A and B is being restricted by the constraint Q2, which is asserting that the second boolean in this valuation must be true. Next, let's consider the situation where this Q1 has been added to the front of the regex. This asserts that the first boolean in the extreme left of this O string must be true. In the last expression, Q1 and Q2 both appear between A and B. Since they are referring to the same valuation, both of these booleans must be true. As we discussed, the workhorse of our algorithm involves matching O regexes on O strings. Let us discuss the possible avenues for implementing and formally verifying an algorithm for this. One possible way to deal with this is to match using derivatives. This technique is purely functional and can be elegant. In the last year's CPP, Zhushko et al. Verified their algorithm for matching lookarounds in Lean using the notion of location-dependent derivatives. The difficulty with this technique, however, is that the derivative size can grow rapidly with the number of characters in the input string. Thus, one has to carefully keep simplifying their expression in order to keep the size manageable. Another way to solve this problem is you to simulate an NFA directly. Our original work on this problem used the notion of an enriched NFA, which had transitions guarded with Oracle queries. Unfortunately, formalizing an NFA simulation can be quite challenging. This is because we have to reason about graphs and paths in these graphs. Additionally, an NFA simulation algorithm would require tracking the set of active states, which is usually done using a mutable array. Our approach is based on the notion of marked regular expressions. This idea can be seen in functional programming folklore, and a nice exposition can be seen in Fisher et al.'s ICFP 2010 paper. We have extended this idea to deal with Oracle regular expressions. The key idea here is to mark letters in regexes to represent active states of the NFA. This is a structured way to represent an NFA together with its active states. Instead of representing the NFA using a separate graph, we use the AST of the regular expression itself. A marked ORegex is similar to an ORegex, except that it may contain marked letters. Notice that we do not allow marks on the Oracle queries. We illustrate the main idea behind marked expressions with the help of an example. The NFA on the right corresponds to the ORegex on the left. Notice that this NFA has certain transitions which are guarded with Oracle queries. These transitions are enabled only if the guards are satisfied. Initially, only the first state is active. We denote this with the token on an NFA and by marking the letter on the left. On the partial input shown on the screen, both of the states are active. Therefore, we mark both these positions in the corresponding regular expression. Upon receiving an additional B, the state immediately following the transition marked A is no longer active. This is also reflected in the markings of the ORegex. In this way, the markings on the regex reflect the active states of the marking of the active states of the NFA that it is simulating. Marked ORegexes are a purely functional way to simulate an NFA. The marks correspond to active states in the NFA simulation. Similar to the technique of regex matching using derivatives, we use a few functions to manipulate the marked ORegexes. First, we have this function which can check if the given expression accepts the empty string. There is the function isFinal, which checks if any of the final characters in the regular expression contain a mark. If this is so, then the given input has been accepted. The function init marks the initial letters. This corresponds to the idea of placing a token in each of the initial states of the automaton. The function shift follows the transitions and moves each mark to the next letter. This is similar to the idea of moving each token on the NFA to its successor state. The function read removes the marks from the letters which do not match the current input character. For the purpose of verification, we assign a notion of semantics to these marked expressions. The denotation of each marked expression consists of the language of words which can be accepted from the marked letters, starting from the marked letters. For example, if we have the regex AB star with the initial A marked, then the denotation corresponds to the language AB star itself. This is because A is an initial character here. Now, consider the case where the B is additionally marked. This corresponds to the case where we could also include letters, the words of the form B, B star, which we obtain by starting from the letter B. Finally, if none of the characters are marked, then the denotation of this is the empty set. This is because there are no active states in the automaton that it represents. Let us briefly look at the algorithm involving how marked regexes work is verified. The main idea is to prove several characteristic lemmas. This involves how functions shown in the previous slide, such as init, shift, read, and so on, change the denotation of the marked regular expression. Nipkow and Treitel have previously used a similar proof technique in their ITP 2014 paper. The main challenge in our setting is that we must deal with oracle valuations. The functions init, shift, and so on require an additional argument in many cases, which is related to an oracle valuation. The characteristic lemmas themselves are also harder to state and less clean. This is because the queries do not carry any marks, and sometimes we need to carefully characterize the valuations that appear on the extreme left or extreme right of the words. We have extracted our Coq proof scripts into executable Haskell code. Our goal is to empirically evaluate the claim that our algorithm is linear in terms of both the length of the input as well as the size of the regex. We have chosen a family of regexes. We can see here that with the increase in the parameter, the size of the regex increases linearly. For these families, we have chosen an input which would elicit the worst case behavior in backtracking based matchers like PCRE. In this plot, we have shown the total time taken to process the string given its input length. The different lines in the plot correspond to different values of the parameter. We can see that the increase in the input string length, the time grows linearly. In the next figure, we fix the size of the input string and show the time taken to match the string for larger and larger regexes. Each line corresponds to a fixed size of the input string. Again, we see that the time taken increases linearly with the size of the regex. We have also observed that the tools such as PCRE exhibit superlinear growth for these regexes. I want to conclude by summarizing the key points of this talk. We have presented a formally verified regular expression matcher which can handle lookarounds. The proof script consists of about 10,000 lines of Coq code. The main idea of the algorithm was to process the lookarounds layer-wise. We match the regexes inside the lookarounds first. Then we use the pre-computed information to resolve the lookarounds. The main abstraction we used was the notion of O regexes and O strings. Thus, we solved the problem of matching regular expressions with lookarounds on strings by matching O regexes on O strings instead. We did this using the technique of marked regular expressions, which are a purely functional way to simulate NFAs. We retain the same efficiency guarantees as that of the original algorithm, namely that it is linear in size of the string and the regex. We have empirically confirmed this by performing experiments on the extracted Haskell code. The proof scripts for this formalization are publicly available. Thank you for your attention.
I don't think, oh yeah. Thanks so much. So I guess the question is the speaker online? Oops, is the speaker online?
Yeah.
Okay, perfect. So are there any questions?
Hi. Yeah, thanks.
Hey.
No?
Hey,
All right.
yes, please.
Yes. Okay, great. So cool stuff. You said a little bit about equational reasoning, using these look around clauses.
Yeah.
Is there any hope at all for a completeness theorem in the same style of Cozen?
I believe that should be possible, but at this moment we do not have this. But I think we are working on it.
All right, thanks.
I do not have many details right now. Thanks.
Yeah.
Hi.
Any
I
other
have a question
questions?
about the complexity of the algorithm with respect to the size of the alphabet. Because you were showing examples with sort of simple examples of A, B, and C, but I'm just more
Yes.
curious about, let's say, if you take Unicode or real regexes, how
Yeah.
would you partition the essentially the predicates that occur in the regex with respect to your algorithm?
Yeah, so maybe I should summarize the question. I think the question is about like, does the size of the alphabet affect the complexity? And the way we have encoded this algorithm is the regular expression to carry predicates. So the atomic elements of the regular expressions are Boolean functions, which will be executed on each single letter. So as long as those functions can be executed in constant time, like the rest of the guarantee should remain.
I was more thinking about typical regular expressions that, for example, involve, character classes like, is a word letter or is it digits or intervals.
Yeah, we should be
So
able to do character classes with the same complexity.
okay. Then
So
I have another question, which I'm wondering about. You mentioned that when you compare to derivatives, that the downside or
yeah.
the vice of derivatives would be that the size grows. But I don't quite
Yes.
see that because depends on what kind of derivative you're looking at. If you take Brzozowski derivative, then you're essentially doing incremental determinization. Then, of course, you're building a DFA. But if you take an Antimirov derivative, then the number of derivatives is actually linear in the size of the regex you start with.
Yes, I think that's true. We could do anti-Mirov derivatives. In fact, like this would be a NFA simulation in disguise. But then we would have to have like the machinery to manage sets and so on. This is why we did not go this route.
Okay, thanks.
Yeah, thanks. Any other questions?
Hi, yeah. So your when you're calculating these lookarounds, did you consider like doing a well, I guess it's a sort of dynamic programming algorithm. Did you consider doing memoization instead so that you didn't have to calculate all of the oracles? Because I would guess that in a lot of situations, you had an example where you had D, E, and then Q1. Unless you have a D and an E, you're never even going to ask what Q1 evaluates to. So you might save a lot of computation that way.
Yeah, that's true. So we have not done this sort of thing for this Coq formalization to keep it simple. But I believe the original paper from last year's POPL has many of these optimizations. And also, I believe there was a version of this algorithm presented somewhere last year, which was based on memoization. It like the authors were Fujinami and Hasuo. So I think that approach is based on memoization rather than going bottom up.
Great. Thank you. Thank you
Yeah,
for your
thanks.
talk. Maybe as a suggestion for next time, it would be great to turn on your camera so we would actually see you when we talk to you.
Okay.
And we'll move on. So maybe give him a hand of applause. It was a very nice talk.
Yeah, thanks everyone.
So we move on to the last. Yes, we need to wire you up. We'll move on to the last talk of this session, which is on further tackling post-correspondence problem and proof generation. And the talk is given by Akiro Omori.
Thank you for thank you for having me here. In this talk, thank you. In this talk, I'm going to present on further tackling post-correspondence problem and proof generation. Let me maximize the window. Okay. And this work has been carried out by myself, Akiro Omori, and my supervisor, Yasuhiko Minamide, both from Institute of Science, Tokyo. Let's start by revisiting the post-correspondence problem, or PCP for short. This problem was proposed in 1946 by Emil Post and is well known for its undecidability. The problem is you were given nest types of tiles. In this example, you were given 3 types of tiles. And is it possible to arrange these tiles in such a way that the top string exactly matches with the bottom one? And in this example, one solution is 0 to 0, 0 to 1, 1. And this is a 0-indexed tile indices. And if you arrange these tiles in this order, you can read the top string 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0. And the bottom string 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0. So you should notice these two are identical, right? So this is a solution, and the answer to this problem is yes, there is a solution. Our study includes formalizing PCP and more in Isabelle Hall. Defining PCP itself is straightforward. Alphabet consists of 0 and 1. Tile is a pair of strings. And PCP instance is a list of tiles. And list of tile indices is a solution if the concatenated top strings is equals to the concatenated bottom strings. Yeah, and so on. PCP SW refers to some subgroup of PCP instances which have exactly S types of tiles, and the length of the longest string on tiles is W. For example, the above 2 instances belong to PCP34, but the below 2 instances does not, because the right bottom one has 4 types of tiles, right? So this belongs to PCP44, and the left bottom one has a word consisting of 5 characters, so this belongs to PCP35. And in this study, we aim to solve all problems in PCP34. Let me review current situation about PCP34. There are about 13 million instances in PCP34 after some normalization. And 20 years ago, in 2003, Zhao solved almost all of them. And 3,170 problems remained unsolved. And several studies solving PCP instances heuristically were conducted after his study, but this is the most comprehensive one so far. In our study, solving all of the remaining problems is the main purpose. But why focus on PCP34? PCP instances with 2 tiles is shown to be decidable. And PCP33, P31, 32, 33 was completely solved in his study. So now PCP34 is the minimum unsolved problem set. And tackling specific instances might help us to get some intuition about the decidability of PCP instances with 3 tiles, right? That's the motivation. These are our contributions. We solved all PCP34 instances except for only 2. So now the figure I showed earlier has changes. I solved 3,168 instances in total, but we still have 2 unresolved problems. And I listed these 2 here. And you can access my website through this QR code and try solving them yourself. And to solve instances, we've developed two novel methods, and I will talk about it later. Lastly, we automatically generated proofs for each instance and verified the correctness of our results. Why does this matter? We've solved 3,168 instances in total using some thousands of lines of code I implemented. And every time I touch the code, I find a new bugs. So when some ask me, are there any bugs in your program, I can't deny that possibility at all. So to resolve this challenge, there are several possible approaches. The first one is to prove the program correctness. And by proving the program correctness, we can ensure the correctness of the output of the program. But we chose another one, which is to generate proofs that can be automatically verified. I mean, we generated 3,168 proofs, separate proofs, and verified those correctness using Isabelle Hall. From the next slide, I will briefly explain how we proved. Proving there is a solution is quite simple. Here, let's revisit the example I showed earlier. I showed an actual solution to this instance either. So how do you formally prove that there is a solution for this instance? So you already know an actual solution to this instance, so you can provide it as an evidence to show this instance indeed has a solution. This can be achieved with a few tactics in Isabelle Hall. On the other hand, proving there is no solution is much harder. To achieve this, we use an inductive invariant as an evidence. I mean, in other words, the existence of this object, inductive invariant, indicates that there is no solution to this instance. Our method automatically finds such an inductive invariant. From the next slide, I will introduce two methods we employed. Before that, let me explain what a transition system of PCP instance is. Considering the transition arranging tiles one by one from left to right, we can define a transition system. In this example, the first tile is arranged, and now the bottom word matches with the first character of the upper tile. So as a result, 0, 1 remains on upper side, right? So we denote this state as upper 0, 1. And by applying the tile, the upper word becomes 0, 1, 1 by concatenating the 1 to the remained 0, 1. And 0, 1, 1 matches with the first three characters of the bottom word. And as a result, lower 1 is the resulting state. In this way, we can define a transition function T, and the state set is pairs of upper or lower and a word on alphabet 0 and 1. Initial states is the states corresponding to arranging exactly one tile, and bottom states is the states having empty word. So now the solvability of PCP instance is equivalent to the reachability from the initial state to the bottom states. This is an illustration of a transition system of the above PCP instance. This is the only initial state of this transition system. And by applying the third tile, it transitions to upper 1, and so on. By following the red transitions, you can see the initial state can reach the bottom state. So this instance has a solution. Here, the most important concept is inductive invariant. This is the name of some state set satisfying these three conditions. First, it crosses under transition. Second, it subsumes all initial states. Third, it doesn't contain any bottom states. If such state set exists, we can say that there is no solution to this instance. here is an example. Let's prove this simple PCP instance consisting of only one tile doesn't have any solution. Obviously, this doesn't have any solution. The initial state is upper 3 ones, and by applying the tile, it transitions to upper 6 ones, then 9 ones, and 12 ones, and so on. Apparently, the reachable states is the pairs of upper and repetition of 3 ones. Reachable states is an example of inductive invariant because it subsumes initial states and is, of course, closed under transition because this is a reachable state and doesn't have any empty word, right? But generally, inductive invariant is not unique, so we can consider another inductive invariant noted here. Yeah, there are several inductive invariant generally. To find such an inductive invariant, actually many methods are proposed for this type of problem. We tried to apply PDR and abstract regular model checking, which is a method to solve regular model checking problem. And we tried termination checker and time rewriting system. And those methods made some success, but our methods overperformed others, so we introduced our methods. There are 2 types of methods. The first one is infix prefix suffix method. This is a method finding a specific type of pattern that every reachable state follows. And in this method, we use a language class infix prefix suffix language to abstract state space. And we have a variant regular language method. This is a generalized version, and it leverages regular language to abstract state space. Let's begin with the first one. To get an intuition, let's observe this case. Lower 011 is the only initial state. And by applying third tile, it transitions to 001100. And please remember 0110 appears here. And disappears now, and appears again. Our intuition says 0110 will never be removed. And if this is correct, the initial state cannot reach bad state, because bad state is a state of empty word, right? To show that, let's consider the state set of words containing 0110 as a substring. We used regular expression here, dot star 0110 dot star. And we can consider applying tile to this state set. The first possibility is the case that the upper word of the applied tile matches with the part of wildcard. In this case, 0110 doesn't match with anything and remains there as it is. And the second case is that the wildcard part is actually empty, and the upper word of the second tile matches with the first character of 0110. In this case, 110 will be the prefix, and the lower word 11 will be the suffix. So it transitions to lower 110.11. In this way, we can transition a state set to several state sets. In this case, eventually it reaches the below state, and as it contains 0110 as a substring, it is subsumed by the root node. So the union of these states is closed under transition. And we call this type of language infix language, and we call this type of language prefix suffix language. We use these 2 languages to abstract states. To find such a pattern automatically, we use some kind of exhaustive search. The difference from the naive exploration is every time we make a new node, we abstract it by choosing arbitrary substring within it. In this case, we chose 1 and made an abstraction node, dot stir 1 dot stir. And we repeatedly attempt to abstract and transition. And if it fails, backtrack and continue exploring until we find an invariant. Yeah, this is the prefix suffix, infix prefix suffix method. And we have a variant called regular language method. In this method, we represent the state as an automaton. And to abstract a node, we merge the nodes of NFA, the automaton. In this example, we make a straight line automaton corresponding to the root node. And by merging several nodes, in this example, by merging Q1 and Q3, we can make an abstracted node. And to implement transition operation node automata, we can use a combination of concatenation and left quotient operation. For example, considering apply this tile to the root node. Since this is the lower state, we first concatenate the lower word 1, 1 to the language of the language LA. And then we need to consume the upper word 0 from left side. And we can express the language like this. Okay, using these two methods, infix, prefix, suffix method and regular language method, we could solve almost all problems automatically. But to tackle instances we couldn't solve automatically, we made a manual invariant discovery tool. By using this, you can find an invariant manually. And users can input arbitrary regular expressions here, and this tool continuously checking the invariant 3 conditions and tells us and counter an example to the closeness. And the user can block the counter example by adding new regular expressions. For example, this is an example I showed earlier. Users can, 111 plus is an inductive invariant. Congratulations. And please solve and resolve the 2 problems. Okay, so anyway, not depending on the method you use, we get a closed graph which looks like this. Specifically, which is a set of state sets, B1, B2, Bn, and the transition inclusion relations, which is, for example, the past state of B1 is subsumed by the B1 and B2 and B3 or something like that. And given this graph, we need to generate a proof which proves the 3 invariant conditions, and there is no solution to the PCP instance. First, we need to define nodes. Then prove relations, then merge the relations to show the closedness and other 2 conditions. Let's start with defining nodes. This is an actually generated definition of an NFA for some regular language. You don't need to read this code. And it just defines a transition function, and by using it, it defines an automaton. We faced 2 design choices here. The first was about the type of automata to use, NFA or DFA. And we decided to use NFA because implementing union and concatenate operation on DFA is inefficient and it's difficult. The second choice concerned how to represent state of NFA. Initially, we attempted to define a new data type for each NFA, but it internally generate n-squared lemmas to distinguish between constructors, right? So, and at most, NFA contains hundreds of states, so it costs prohibitively. Finally, we chose to use binary representation of natural numbers. And as you can see, it has only 3 constructors, and you can easily distinguish between values by comparing digit by digit. Okay, so the config, this is the state, is a pair of upper or lower and the word on an alphabet. And we can define a node using the defined automaton. Okay, we successfully defined the nodes. Then let's prove inclusion relations. Here, all vertices were given as NFAs. And we need to prove a lemma-like post state of V1 is subsumed by the union of other nodes or something like that. To do this, we need to implement union operation. And this is easily done because we decided to use NFA. And we need to implement transition function on NFA. And as I mentioned earlier, this is realized by the combination of concatenation and left quotient operation. And both of these two can easily be implemented because we decided to use NFA. The hard part is the procedure of inclusion checking between NFAs. To do this, we used anti-chain algorithm. This is essentially on-the-fly DFA construction. But we didn't want to prove its termination property, so we didn't. What we did is defining step function of this algorithm and proved some invariant holes when stepping the algorithm. And the actual computation is done by transforming a subgoal. This function, this state invariant function, is immediately simplified to true when the algorithm terminates. Okay, so we proved inclusion relations. Finally, we need to match those relations to show the closedness and other two conditions. Closedness is proved by combining inclusion relations. The second one is proven by checking acceptance for each element of I. You can do this because initial state is always finite set. The third property is proven by checking acceptance of epsilon for each of automata. Using those lemmas, we proved the existence of an inductive invariant. Finally, using the manually proven lemma, which states there is no assertion if an invariant exists, what a clear name of lemma. And we can show that there is no solution by combining the existence of inductive invariant. We implemented algorithms and proof generators in Rust language. And some proofs were too large to build due to timeout or out of memory. Please note that this doesn't mean we still have unverified instance, because we assume an instance is, the result of instance is verified when one of two equivalent instances, original or reversed one, is verified. Reversed instance is just a reversal of the original instance. And considering arranging tiles backward, you can easily see these two instances are equivalent. Okay, in conclusion, we proposed novel algorithms and solved all PCP'24 instances except for 2. And we verified those results formally. As for future work, first we need the remaining 2 problems. We need to solve the remaining 2 problems. Second, our algorithm was applied only for the problems which is unresolved in Zhao's study. So we need to formalize his result. And once we successfully resolve all instances in PCP'24 and verified those correctness, we'd like to prove such a lemma, such a wrapping up lemma. This states every instance of PCP'24 is unsolvable, or the shortest solution has at most 452 tiles. And it suggests that we really solved all instances. So we'd like to prove such a cool lemma. Okay, this concludes my presentation. Thank you for your attention.
Thank you. So are there any questions? Claire.
Thank you for the talk. Sorry, I forgot my question. Yeah,
Which slide?
Yeah.
On here.
Yeah, I got it.
This one?
So
Yeah,
so
okay.
in your benchmark, in the graph things, in your implementation, why does the reversal change the runtime?
Reversal.
Yeah,
the
tile
reversed instance. So
oh.
your question is the
Yeah.
transition system no reversed instance is different from the original one.
Yeah, why the runtime is different or memory consumption is different in terms of the when you reverse the tiles.
Yeah.
Is there any like suspected reason of that?
Actually, I can't find any reason, but actually the original and the reversed instance has completely different transition system, but these two are equivalent. So yeah, I feel this is interesting. Is that the okay? Sorry.
Hi. I wonder, in this checking of the proofs, you are using everything you run Isabelle build. So you're not generating externally code and then run it natively in a language. So to which extent do you use the eval method within your proof scripts? Or could you somehow use some verified automata library which then runs more efficiently than running proof scripts within Isabelle?
So your question is why I didn't use such an existing automata library or something? No.
Not why you didn't use it, but would it be feasible to use it, and to which extent do you use the code by eval method, so to use reflection and run generated code for proofs?
So yeah, we could generate an exact type of code, yeah, actually, but we didn't because we would have likely to the fact in the Isabelle whole world. So so if I generate some exactable code outside of from Isabelle Hall using Isabelle Hall code generators, we can, yeah, of course we can check some correctness of the certificates, but we'd like to have the correctness. We'd like to show the correctness within the Isabelle Hall. So is that understandable?
Perhaps we discuss offline then.
Okay, sorry.
Do you have any theoretical results on like the completeness of this method? So like you're using inductive invariance, like are there any guarantees that you will be able to find all of the solutions eventually if you were to just enumerate all possible invariants that are regular language?
We don't have. If this method has such a completeness, it means we solved the decidability problem of PCP instances with 3 tiles.
It could still be semi-decidable. Like there are an infinite number of invariants.
Semi-decidable. Yeah. So our method is to show unsolvability, right? So, and PCP instances with 3 tiles is the desirability. No, PCP instance with 3 tiles is an open problem, and no one knows our method is complete or not. So, yeah, we can say we can't say such a thing.
Thank you. I had one more question, maybe. So, I mean, you've solved this problem with this particular technique for PCP 3.4, but I'm wondering how the same kind of approach does it apply to these other classes you have there? Does it, and in some sense, does it scale, or is it universal in that sense?
PCP for 3 or other kind of classes. Yeah, of course, this will be scalable and is applicable to such kind of other classes. But I haven't applied comprehensively yet.
Okay. All right, well, let's thank the speaker. And we'll see you all tomorrow morning at 9 o'clock, right?